Hello, am I audible?
Yes, ma'am.
Okay. Good afternoon, Sachin sir.
Good afternoon. Good afternoon.
Good afternoon, everyone. I, Dr. Amrita Ruperi, coordinator of this course, on behalf of Electronics and Telecommunication Engineering Department and Vidyavardhani's College of Engineering and Technology, I welcome you, sir. And
Thank
now
you.
I invite Kanchan Madam to take over the session.
Thank you, ma'am. Good afternoon to one and all. Welcome to the last day, 11th session of AICT sponsored ATAL Online Faculty Development Program on Quantum Intelligence, exploring the convergence of quantum computing and artificial intelligence. I, Kanchan Sarmarkar, on behalf of the organizing team, take this opportunity to warmly welcome our speaker, Mr. Sachin Namdev, who will be delivering the talk on the topic Quantum Transformer and Quantum Federated Learning. Mr. Sachin Namdev is a researcher with an expertise in hybrid classical quantum machine learning, currently working as a project engineer in the quantum computing group at CDAC. He holds an MTech in computer science and engineering with specialization in artificial intelligence from DIIT Pune, where his thesis focuses on quantum long short-term memory network. At CDAC, he has been actively involved in the research on quantum convolution neural networks, exploring the integration of quantum computing with modern AI architectures. His work contributes to advancing quantum advanced learning models and developing algorithms at the intersection of quantum computing and artificial intelligence. It is our great pleasure to have you with us today, sir. May I request you to please start the session. Over to you, sir.
Thank you. Thank you for the introduction. Let me just share my screen. I think you'll be able to see my screen.
Yes, sir.
Yes, sir.
Oh, okay. Let's start. Okay. So, good afternoon, everyone, and welcome to this talk on quantum transformers, quantum federated learning, and a little bit more on real-world applications in QML. So as you know right now, you are using Chat GPT, LLMs, and large language models, even Gemini. So those architectures or those LLMs are based on classical transformer models. Basically, what is a transformer? Is nothing but a decoder only model of the of the autoencoder models. So you have autoencoders which encode your information and decode information. So the decoder part, if you take that and you create something known as transformers. So let's move on. Basically, before we get into quantum transformers, there are some key terms which are used in transformers, especially classical transformers. Basic thing is a token. A token is nothing but a basic unit in a sequence like a word, subword, or image patch if you have image transformers, or time step if you have temporal transformer, time-based transformers that the transformer processes. So basically, if you are able to see my mouse, basic unit would be nothing but a word or something known as a you can have a subword, which in case if you have multiple words like playing, so that play plus ing, those are two different subwords of a word. Then you have something known as query. Query is nothing but the question a token asks, what kind of information do I need from the other tokens? So what kind of, let's say this is the token, it would ask what kind of information is required for this token in comparison to other tokens. So this in this, for example, in this, a token is a basic unit in a sequence. So token is connected to basic unit and sequence. So these all three are the answer to this question. What kind of information do I need from other tokens to ensure that this word or this token has meaning? Key. A key is the label a token carries so that the other tokens can check if it matches what they are looking for. For example, again, let's take this example again. This token, now it would have some key values which are connected to this. Now the thing is, token is a basic unit. This is its meaning. Where in a sequence. So this word has labels connected to these words, or you can subsequently say that these words or tokens also have connected to connections to this. Value is the actual information a token shares when another token decides to pay attention to it. Basically, again, let's take the example here. If this is the token, how much it is connected to this token, or this token is nothing but the value. So if token, since this is the basic unit or the actual definition of it, so it is connected more towards these tokens and more towards this because it tells in what or where. That's basically a sequence. So this is connected to this and this in a much more value. It can be 1, it can be 10 as compared to these basic tokens. So that is query, key and value. These three things are much more used in transformers. Then you have something known as attention weights. Attention weights are scores that tell how strongly one token should listen to each other token. It is basically calculated from all these three. It is an amalgamation of all these three, which gives it a value, basically a similarity value. How much similar is this token to this token to this? Basically, these two have much more similarity value as compared to other. So these are some of the key terms in transformers. So why do we need transformers in quantum machine learning? So basically, if you see a classical transformer, this in this image, if you see, this is the, what can you say, architecture of a classical transformer. So you have inputs, you embed them, basically convert from these words to vectors or the numerical representation of them. Then you give them positional encoding. You encode according to the position as well. So for example, this classical transformers, this classical is the first position, transformers the second position. That also needs to be encoded. Then it goes into a multi-head attention. Now what is multi-head attention? Basically think like you have multiple QKV matrices which gives attention weights, which transforms these models and tells how each token is connected to each token, what is the meaning of each token. And multi-headed basically means each this QKV is there in one head. So multi-head basically means two or more heads are there. Basically two or more thinking, you can say like two or more brains are there in one multi-headed attention. Then you have normalization. You add them, basically amalgamation of multiple different outputs, how one person, how one brain thought, how other brain thought, and then you put them together, amalgamate it and normalize it basically. So because these are vectors, so you have to normalize them so that they do not explode. Okay, because here processing would happen and they might explode, meaning their values might go very much higher. So then you normalize them and then you give it to a feed forward neural network which tries to decode the information basically from those vectors. And from those vectors, you get the words. So this is how a transformer basically works. So classical transformers solve sequence. You have in basically like ChatGPT, vision, basically like vision models, image generation models, and multimodal task by learning data dependent token interactions via self attention. This QKV and attention weights give you the self attention, basically telling how much attention should I give to one or multiple tokens. Now, what do the quantum transformers try to aim? Basically, we would replace some linear maps, QKV projections. Basically, the thing is, QKVs are nothing but weight matrices. So if you can replace these weight matrices by using quantum circuits, you would have a quantum transformer. Basically, a hybrid quantum transformer, but still a quantum transformer where most of the, what can you say, processing would happen in the quantum circuits with parameterized quantum circuits. Basically, your quantum circuits with parameters, the rotational gates. You may have heard PQCs a lot if you have jumped in quantum machine learning. PQCs are nothing but parameterized quantum circuits, where quantum circuits have parameters, rotational gates, where you can change the theta or accelerate parts of quantum attention via quantum subroutines. Basically, for example, if you do not want to use QKV projections, you can use similarity fidelity test also, where each multi-head would find out the fidelity, basically similarity measure of each token to other token. That is also a one way of quantum transformers. Now, what are the benefits? Rich feature maps from quantum evolution. Because if you have, let's say, 4-qubit quantum circuit, if you take 4-qubit quantum circuits for your quantum transformers, they live in 2 to the power 4 dimension. Okay, so with this higher dimension that is there that we can use with quantum circuits, you can see, or you can basically process these tokens in a much better way as compared to classical transformers, and potential parameter savings as well. Now, if you see multi-headed attentions, these are QKVs. Now, if dimension increases, okay, the QKV size also increases and the parameters also increase. But if you use a quantum circuit, even if you use, let's say, 2 to the 4 or 8 qubits, it is still a very high dimension data that is being compressed into a very small quantum circuit, which would help you to save parameters. That means the amount of trainable parameters, and hence training would be much more faster. Your model would be much more lighter, and you can use that not even just in with GPU, but in CPU as well. But the constraint are limited qubit counts. The thing is, with any classical device or anything, you cannot scale beyond some 30 or 35 qubits. Otherwise, you would need a very much, what can you say, higher HPC, very high powered computers with RAM in basically going above 2 TB, 2 terabytes. Even if you say, if 32 qubits, if you say I'm going to run 32 qubits, that requires 1 TB of RAM to run that. And if you add one more from 32 to 33, that doubles the resource requirements. So doubles the RAM, doubles the computational time. So that is why we are still limited to the qubit counts. Then there is noise. As you know, today's era of quantum computers are noisy. So even though we can use simulators, but if you want to actually deploy it to a quantum computer, there would be noise. And as you increase the size of your circuit or the depth of your quantum circuit, the noise would be increased. Thus, it forces the quantum transformers to target small token counts and relatively low sequence length, very basic like 10 or 20 sequence, or if you are using amplitude encoding to compress it, 2 to the power n, basically meaning the number of qubits you take. Now we move to classical self-attention. Now the thing is, how is self-attention calculated? Basically, let's take this as an example. I hope you're able to see this. I love tennis. Okay, these are 3 words. Now what happens is, these 3 would be converted to input embeddings. Basically, they are vector representation. And then these would be given to attention head, where basically it would be multiplied with WQ, which is nothing but the weight of the query matrix, WK, which is weight of the key matrix, and WV, which is weight of the value matrix. When they are multiplied, You would calculate attention scores based on these the Q and K accordingly like this. Then you'll take the softmax. This D, root D is nothing but the dimension of your matrices. So if it is 4, so it would be root 4 of the key matrices. Then you would get attention scores. Then these attention scores along with the value would give you the context aware embeddings, basically telling you how each and everything is connected to each other. So basically in a normal transformer, you start with a sequence of tokens. It can be words, it can be image patches as well. These need not be words, these can be image patches as well. So these would be replaced by the pixel values and time steps, basically time, or basically if you want to use transformers for time series analysis, so that can also be done. Then for each token you build 3 different vectors using learned matrices: query, key, and value. These things go into one head, and you would have multi-head in there. You can have 2, 3, 4, or even 12 heads per multi-headed attention. And you can even stack these layers one upon another to create a much more better transformer model, which now we call it large language models. And then you decide how much token I should be paying attention to token J with by computing a similarity score via this. And then you softmax all over J, then you get the attention weights and use them to average the values. This Vj is nothing but this calculated values. So self-attention is learn QKV, then compute similarity between Q and K, and then use those weights to mix the V's, the values. So this is classical self-attention. Now, what changes in quantum? You want to convert the classical self-attention to quantum self-attention. One of the ways to introduce quantum transformers. So basically in quantum self-attention, you keep the idea of query, keys and values and the weights, but you let a quantum circuit do some of the heavy lifting. So these weight matrices are now replaced by parameterized quantum circuits. So the way would be the same thing only. You would encode each token xi into a quantum state using any feature encoding, angle encoding, amplitude encoding. Then run a parameterized quantum circuit, PQC. Here you have encoded that and you would give it to this, where UQ is nothing but the quantum circuit for query, UK is quantum circuit for key, UV is quantum circuit for value. Then you measure the qubits to get the classical numbers that act like QKV or similarity scores. Basically QK, then you untangle this. When you untangle it and you do measurements, you get the QK value or the similarity matrix. Then you again untangle this and then you measure it again, which gives you the scaled dot product attention, which is nothing but your classical numbers. So different papers choose different parts of this pipeline to quantize. Some recent survey groups them as QKV only, basically where you encode Q, K, and V as basically quantum circuits. Pairwise quantum attention, where you do not use these QKV, you basically try to find out the scale dot product directly. And fully accelerated quantum attention, where instead of going one head at a time, you go globally. We'll see them all these three one at a time. Okay, so this is some classical versus quantum self-attention comparison. Basically, some aspect where it runs. Classical self-attention can run entirely on classical hardware, but current quantum self-attention is hybrid, where classical part plus some quantum circuits on simulator or on quantum devices. Input representation tokens are real vectors, but in this tokens are encoded into quantum states. How QKV are built? Linear projections are there, basically your Q or query would be X, your tokens, multiplied by WQ or the weight of the query. Similar goes with key, similarly with value. But in this quantum self-attention, you have parameterized quantum circuits or quantum kernels. This is one of the other ways to use it without where you can use quantum kernels as well for quantum self-attention, where you encode the token, apply the PQC, then measure to get the QKV or similarity scores in the case of quantum kernels. You would directly get the similarity scores without having QKV in quantum kernels. Then similarity computation, dot products is there in the Euclidean space. Either dot products on quantum generated vectors, QKV, or overlaps and kernel values in quantum feature space, basically similarity scores, direct similarity scores. The attention weights are nothing but softmax over similar scores in classical. You can typically use softmax, but if quantum scores come from quantum measurement or quantum subroutines, you can directly use them. Just as the case in quantum kernels. Expressive power, very strong for large models and data, but purely classical feature space. So if your data is in D dimension, it is still in D dimension. Potentially richer feature maps from the Hilbert space of quantum state. Basically, if this was D-dimensional data and you convert this D-dimensional data here, it is now in, if you use the same amount of qubits and same amount of features here, this would be in 2 to the power D dimension as compared to simple D dimension here. So this is much more in a much more higher dimension, you can say, and much more richer feature maps and richer ability to see the connections between two different tokens. Training would be standard backpropagation and fully differentiable, but this is hybrid training, as is the case currently right now. Gradients through PQCs you would get via parameter shift rules or any similar thing, similar like Cobila SPSA, which is affected by noise and barren plateaus as well, which is still there in the quantum ML. And usually a small depth and qubit counts would be there in the quantum self-attention. Hardware assumptions, it is mature currently, and it is mostly NISQ or noisy intermediate scale quantum devices are there. Maturity of the ecosystem, very mature is there. You have transformers that dominate NLP like ChatGPT, Vision, where you can generate models or you generate images, or you can use images to get prompts. Audio is there, and multimodal, basically having multiple models which do, like one would do Google search, one would try to get the information from that Google search. So all of these are there. But this quantum self-attention is still in the early research. Quantum self-attention neural networks, quantum self-attention networks, quantum kernel self-attention networks, and other things which are mostly proof of concept on very small data sets. So now we come to how you can create quantum self-attention via one of the ways, QKV only PQC mapping. Basically, query, key, and values are now each converted to quantum circuit. So you have quantum circuit for query, you have a quantum circuit for key, you have a quantum circuit for value in each of the heads. Basic idea is we keep the overall attention pipeline classical, but compute QKV using quantum circuits instead of linear layers. This is sometimes called QKV only quantum mapping. Now, if you see here, basically here your data would be given, encoding would be there, angle encoding, amplitude encoding, or you can use much more like ZZ feature maps or poly feature maps to encode your data. Then you have a PQC, which is basically your processing unit. Here, this, if let's say this is your PQC, these Rx and Ry as well as the controlled Rx gates would have some theta. This theta would be tunable via iterations, just as there's a case for any classical machine learning, where you have parameters which you tune using iteration by having optimizations. So here this processing would happen in such a way that the thetas after n number of iterations or after optimizations would give you the exact values of QKV. And this is for each Q, K, and V. Each you would have 3 different circuits. Now, step by step would be encode the tokens as a quantum state via this. Take the token embedding, basically a small vector would be here. Use it to set rotation angles in a quantum circuit, for example, Rx, Ry, Rz on several qubits. After the encoding, you have a quantum state that represents a token in a high dimensional Hilbert space. Basically here, you can have data encoding. You can use the same thing as well for data encoding. And here you would get the encoded state of your tokens. Then you run a parameterized quantum circuit, basically this, apply a trainable unitary. This is nothing but a trainable unitary. Why? Because the thetas are trainable, the thetas are tunable. And the parameters or the thetas would act like weights, and they are similarly updated via gradient descent methods or SPSA, which is a non-gradient descent method similar to classical networks. Basically, nothing changes. Everything else remains the same. It's just that now a quantum circuit is acting like a weight matrix where these Rx, Ry, and Rx, Ry, whatever the parameters they have, are now your final weights after training. Then you measure to obtain the numbers. You measure here, you would get expectation values of some of the observables. Basically, let's say you are going for these 2 qubits only. You would measure them, and that measurement would give you a classical vector where that would represent either Q for if you have quantum circuit for query, K if you have quantum circuit for key, and V if you have quantum circuit for value. These expectation values form a real valued vector, and we interpret these vectors as the query, key, and value representation for that token. If let's say this was given for QKV, and whatever the outputs came after measurements is nothing but the query, key, and value representation for that token. Now, why do you need to do this? Basically, the quantum states live in a huge Hilbert space. Hilbert space can go up to infinite dimension. Even with a few qubits, the space of possible states can be very rich. If let's say I'm only using 4 qubits, now my data is in 16 dimension, 2 to the power 4. If I use 10 qubits, my data is now in 1024 dimension. So it is a very much, you can exploit this Hilbert space with very few qubits. The QSANN paper, basically quantum self-attention neural network paper, shows that such quantum generated features can help text classification and outperform some classical baselines, at least on very modest scale task, because the number of qubits is limited. So you cannot have very much higher dimension, much more bigger dimension data that you can give. You cannot give the whole novel in one go. You would still have to give like either a few of the tokens in one go rather than the whole novel itself, which is currently available in classical transformers. And because the tensor formula itself is a dot product plus softmax, it stays classical. Thus, this variant is easier to implement and benchmark. So if you use this QKV only PQC mapping, it would be much more easier to implement that and easier to benchmark it against classical baselines. Trade-offs, pros is easy to plug into existing transformer code. You are basically changing nothing. Only thing is the query, key, and value matrices are now nothing but quantum circuits. It is straightforward to compare with the same size classical baseline. Replace PQC with a small MLP of the same parameter count. Basically, if you have classical transformer and you use quantum transformer, if you have comparable parameters in the PQC and the classical, it would be much more straightforward comparison. But cons is training PQCs can suffer from barren plateaus if circuits are too deep. Now the thing is, you have to create your quantum circuit in such a way that you get much more accurate outputs. So for that, you have to create a deeper circuit. And the more deeper circuit you create, the more it is prone to barren plateaus. Basically, the gradients would be zero. Your training would not happen, and your quantum transformer won't be as much effective as classical transformer. Simulation is expensive. You use many qubits. Other thing is you have 3 quantum circuits per head. And if you use more heads and deeper circuits, so it takes much more time to train it, and you would have a much more deeper ansatz. So currently in simulation, it is very expensive. So in practice, these are very small models. Even if you go with quantum transformer models, they would be much more, they would have 4 to 8 qubits, which are very much faster to simulate and faster to train as compared to having more like 30 or 40 qubits. Now, how do you do that? You in QKV mapping, you had 3 quantum circuits per attention head, which is very expensive. So you use something. There is another method. You use pairwise quantum attention, basically similarity computed in a quantum circuit. Sorry. Similarity computed on a quantum circuit. Instead of 3 quantum circuits, 3 different quantum circuits, you would have one quantum circuit where it would try to find out the attention scores. These scores, this score directly, instead of having these three with these 3 quantum circuits. The quantum circuit would directly find out this. So how does that happen? Instead of using quantum circuits just to build Q, K, and V, we ask the quantum device to compute the similarity between token states directly. Earlier we had Q, K, and then V to find out the similarity. Now we would use the quantum circuit itself for similarity measurement. The idea is you encode each token as a quantum state just as before, and you compute how much token I should pay attention to token J via quantum similarity test. You can use a swap test. Basically, a swap test would have a Hadamard layer, basically a single Hadamard gate on ancilla qubit or auxiliary qubit with a controlled swap. You control it via the ancilla or the auxiliary qubit on each of the states. So this here is nothing but your token, or it can be a different words, sentences, multiple sentences as well, where you are going to connect the first word of the sentence to the first word of the other sentence. Similarly goes with second word, third word, up to all the n words, basically via swap test. And quantum kernel methods as well, basically any quantum kernel, sets of quantum kernels, where you would define a kernel via this and then estimate with a quantum device. So let's see a little bit about swap test. Now, measuring fidelity. Fidelity is basically the similarity score in quantum terms. Fidelity is nothing but the similarity of 2 quantum states. Your core idea is basically prepare copies of the states and tangle them with an ancilla via H, control swap H. So basically, if let's say these two are the qubits for you can say word 1 or sentence 1, and this is for sentence 2 or word 2. Here Q1 would be the first word in the sentence of sentence 1. Q2 would be the second word in the sentence of sentence 1. Q3 is nothing but sentence word 1 of sentence 2. And Q4 is word 2 of sentence 1. And then you would have an extra qubit, an ancilla qubit or auxiliary qubit, where it would be controlled via Hadamard gate, and you control you have pairwise C swap gates connected, which is controlled by your ancilla. So what would happen is, if let's say here is Hadamard gate, so you would have 2 possibilities, either 0 or 1. If it is 1, its controlled swap gets activated, and Q1 and Q3 would then swap. Similarly, then Q2 and Q4 would swap. And then after this, you would measure here. Now the thing is, when you measure here, you would see the probability of having 0 in here. If probability of having 0 is 1, then you try to find out fidelity using this formula. 2 into P0. Now the P0 is 1. So 2 into 1 minus 1, which gives you the value of 1. That means the highest fidelity. Fidelity ranges from 0 to 1. So 1 being the highest fidelity, basically meaning those two quantum states which were encoded here are same or similar. And using this way, you would find out the fidelity or the similarity scores of each and every tokens. Can be in sentences as well. But the resource constraint is you have one ancilla qubit plus two n qubit data registers. If you have d dimension data, okay, let's say d is 2. So you need 2 plus 2 plus 1, or 2 into 2 plus 1, 5 qubits, which is very expensive. If this went to 3, dimension went to 3, so 2 into 3 plus 1, which is 7. You are increasing your qubit count by 2, approximately by 2, by adding one dimension to it. One increase in one dimension adds 2 qubits, which is very much expensive. But the typical use case of this method is gives you exact fidelity of two pure quantum states. And this is hardware agnostic. It can be like this quantum circuit can be run on actual quantum hardwares very easily. And it is very conceptually simple. It's just these gates, one Hadamard, multiple control swaps which are connected to each of the dimensions, and then another Hadamard. But it requires preparation of both samples at the same time. You would have to prepare these two samples at the same time, and doubling the qubit needs as the number of data qubit grows. As I said, if your dimension increases by 1, so your qubit needs also doubles. Basically, for 3 you would require 7. 2 into 3 plus 1. And the circuit gets deeper and harder to run as you have much more bigger what can you say, dimensional data. So this is one of the ways to find out the fidelity. So how do you do pairwise quantum attention? Step by step, basically encode and encode J into psi J, basically encoding 2 of the tokens into 2 of the quantum states. Then run a joint circuit that acts on both the states, for example, swap test, basically this, or some PQC that mixes them. You can use this test, or if you have ZZ feature map that can also find out the fidelity for you, you can also use that. Then you measure the outcomes, and from the measurement statistics, you estimate a similarity score. In the case of swap test, you estimate similarity score via this method. And then you use these as the entries of the attention matrix before softmax, instead of using QKV. And the rest is still classical. You apply softmax along each row to normalize the attention weights, combine the output value vectors to get the final output. Now, why is this interesting? The similarity is computed in the quantum feature space, which can represent complex correlation between the tokens that might be hard to capture with simple dot products, which is there in the case of classical transformers. And this is conceptually close to a quantum kernel method, but integrated into the transform. So this pairwise quantum attention can also be termed as a quantum kernel method. Trade-offs is it makes the most of the quantum feature space for pairwise relationships, but can be interpreted as doing attention directly on the quantum kernel space. But cons is you need more complicated circuits that take pairs of tokens. If you see this is very simple, but if you try to use much more different quantum circuits for fidelity measurements, that would be much more complicated. And computational cost can grow with the number of token pairs. So if you have a very long sequence, you need a lot many number of pairs. If let's say this is there, so this would be connected to all these. You would take this and then find out the similarity with all of these. And you take this, then again you find out the similarity. So this becomes very much computationally expensive. And thus for long sequences, this becomes expensive on NISQ hardware. So there is another method, global attention and acceleration method. Your whole attention matrix via quantum algorithm. Basically, you give the whole thing to the quantum attention, whatever the quantum circuit is, give the whole, what can you say, sentences or tokens, or the pairs of tokens, sequences of tokens to the quantum circuit itself. So if let's say this is there from x1 to xn, you would give that as the input in one go to the quantum circuit. The recent survey of quantum transform draws a clear line here. PQC based approaches, what we discussed, have QKV mapping and pairwise attentions. And in this case, you can use quantum linear algebra based approach. This is one. You can also use quantum linear algebra based approaches as well, which are more theoretical. If you see here, the size of the quantum circuit would be much more huge that you cannot use it in classical simulations and as well as in actual quantum hardware that use block encoding quantum singular value transformation and amplitude estimation. You basically have all the tokens given at one go. So if you have 30 tokens, you would need 30 qubits. But if you have more than, let's say, 100 or 200 tokens, so your qubit size would be 100 or 200 tokens depending on whatever is the size. If you have n tokens, n qubits, so which is very much, you can say, impossible for a classical computer to run it, but it is also very impossible for current quantum hardware to run it. Because the thing is, even though we have 128, 256 qubit or even 1 million qubit that you have seen in, for example, in Microsoft Majorana, even with those number of qubits, the useful or usable qubits is very low. So you cannot use this. It is still theoretical. But if our quantum hardwares mature enough, then this method can be used for quantum transformer. So basically quantum global attention in the classical transformer, a big cost is multiplying large matrices like K transformer and then softmaxing with V. QLA based quantum linear algebra based quantum transformer would try to encode the entire vectors or matrices as quantum states. All this would be, let's say this is the whole input, would be now converted into quantum states in one go. Use quantum subroutines to perform matrix operations or approximate softmax. Some quantum subroutines would be there. For example, just again fidelity based measurements, but on a very large scale, potentially with polylogarithmic scaling in some dimensions under strong assumptions, but it is still very theoretical. For example, you would treat this as a matrix implemented via block encoding, just like this, and use QSVT or any related techniques to apply a function to its spectrum, basically the eigenvalues, and then use amplitude estimation to estimate the sums or expectations that appear in the attention head. But the current scenario is these methods are mostly theoretical and assume fault tolerant machines, which is currently not there. Precise state preparation, which is very much tedious task to do, and deep coherent circuits. Basically, your quantum circuit's depth would be much more bigger, and it needs to be coherent. Basically, if two qubits are entangled, they need to remain entangled for a very long duration of time until and unless the quantum circuit has fully run. And these methods are not NISQ friendly yet. Basically, today's quantum hardware cannot support these kind of things, but they point to what quantum transformers might look like in the long-term future when the quantum hardware matures. So basically strategies for quantum self-attention are basic comparison, QKV only mapping, quantum pairwise, quantum global attention, and quantum assisted acceleration, which is still using some QSVT or any related techniques. Where would the quantum part? It is at the feature projection stage before attention, basically QKV, at the similarity computation step, basically when you get the similarity scores, global mixing of all tokens in a single quantum block. Basically, all the tokens are given at the same time. Basically, like giving the whole novel at the same time. At the level of entire matrix operations. Again, in the same way, but instead of using quantum circuits, you would use quantum linear algebra. What is quantumized? PQCs, where Q, K, V are converted to quantum circuits. In here, you would have similarity between pairs of tokens, basically like quantum kernels. Here you would have very large PQCs, very much like 100 to 200. Basically 100 to 200 is very small. You would have thousands or 2000s or maybe more qubit PQCs that will mix all the token embeddings at in one go. And in this, you would use quantum linear algebra to accelerate the parts of attention pipeline. You can use amplitude estimation as well. Attention computation is still classically done because we have QKV, which give us the values, and then we do dot product plus softmax. But in this quantum pairwise, similarity is estimated directly by the quantum circuits by overlaps or kernel values, and then you can use softmax and value mixing are much more classical. Attentions like information flow emerges from the circuit. The whole attention block is computed in one go. And you use quantum algorithms to approximate the matrix multiplications. Typical use cases, quantum QSAN, quantum self-attention neural network style models, QSAN, quantum self-attention networks, or QKSN, quantum kernel self-attention networks. Sasquatch tech, it is basically what can you say, theoretical model of a quantum global attention. And but this quantum assisted acceleration is still theoretical, which proposes that asymptotic speedups would be there, but it is still theoretical, not practical. NISQ suitability would be very high for QKV. It is medium for quantum pairwise, as it requires circuits pairs to be run again and again. Quantum global attention would be low to medium because you need very big circuits, which is very not feasible in NISQ era. And quantum assisted acceleration is still theoretical with very big quantum circuits, so it is still very low for NISQ suitability. Now the thing comes up, how do you encode your tokens into quantum circuits? The encoding strategies. You have angle encoding. Basically, the idea is numbers control the rotation angles of single qubit gates. Say the simple thing is, suppose a token embedding is x1, x2, and x3. We use 3 qubits in angle encoding. Whatever is the dimension of your data, okay, you use the same number of qubits. Thus, on qubit 1, you would apply ry or rx, rz, doesn't matter. On qubit 2, you would apply again rx, ry, rz with x2, x1, and x3 acting as the theta for your conversion from classical to quantum. Why it is popular? It is very much simple to implement. If you see here, I only need a rotation gate and my data is now acting as the theta for that rotation gate. Thus, it is very much simple to implement and it would work well with Penny, which is one of the very good libraries for quantum machine learning. QSKit, which is also one of the good libraries for quantum computing. Then you have TensorFlow Quantum, which used to be a good library, but currently it is now. Excuse me. Okay. In here, circuits stay relatively shallow, so they are more realistic for NISQ devices. But the downsides is it uses one feature per rotation. You need one feature per qubit. Okay, so vice versa is one qubit per feature as well. And if the embedding is large, if this is very big, we need either more qubits or some compression mechanisms like linear layer before encoding. So you would compress, if this is in tokens embedding is very big, you would use classical methods to compress them, and then you would give it to angle encoding. Other idea is amplitude encoding. Basically, you take the embedding vector, you normalize it so that this is there. Sorry. So that when this is normalized, all of them sum to 1. And now all of these are given as prepared as quantum states via this method. Vi is nothing but the value of your token, and I is nothing but the state, where I are the basis state of log 2 n qubits. So basically, if you have embedding vector of size 1024, so you would need 10 qubits to basically encode them. Thus, it is very much compact. Basically, a very high feature dimension would has now been converted into very low feature dimension. With n qubits, you can encode 2 to the power n amplitudes. But the cons are state preparation can be very deep and complicated, especially if you want exact or efficient mapping. And this depth of amplitude encoding is very hard or very difficult for NIST devices and can cause barrel patties. So simple rule of thumb, what you want to do is you want to have small models for teaching labs, start with angle encoding. But if you want to do advanced experiments or simulations or researches, you can explore amplitude encoding, but expect more circuit design work. So you would have to work more on the circuit design aspect of amplitude encoding itself as compared to the processing part of your quantum circuit. Now the thing comes up, how do you encode the position itself? Now we thought about encoding these like this in qubits. But what if we want to encode the position as well in the quantum space? So basically, there are two main ways to bring position information of QML. Classical position encoding before quantum encoding. So before even you encode it, you have taken classical position encodings in your embedded vector. Exactly like in a standard transformer, you would have take the token embedding vector, add or concatenate the positional encoding via sinusoidal or any learned method, and then you feed this combined vector from this and this into the quantum encoder. Pros, it is very simple and directly reuses all the classical transformer tricks. So basically, it also creates a very simple mapping because everything is already done and you can directly encode them, and keeps the quantum circuit designs unchanged. So you need not change your quantum circuit design to have position encoding in there as well, and only the input numbers change. So basically like this, if let's say this is positionally encoded as well, so you would just have to directly use rotation gate. You need not do something with your or change the design of a quantum circuit so that position can be encoded. In this method, this is usually default choice for hybrid architectures. So if you go and try to find out quantum ML transformers, QML transformers, or quantum transformers, you would see that this is mostly used. But what if you do not want to use classical position encoding? So you can still do that inside quantum circuit, but there are two different ways to do that. You basically keep the embeddings as they are. So whatever, you do not add position embedding to it. Whatever is your embedded or encoded vector from basically these words to the classical version of the vector, you keep them as they are, but build the position into the circuit itself. Now your quantum circuit or the design of your quantum circuit would now act as the position encoder. So two options. First is to use extra rotations whose angles depend on token index. Basically, just as we have encoded this information here, I would add one more layer of rotation gates where I would rotate via add an additional RZ or any rotation gates where alpha is a learned or sinusoidal function of a position. Basically, let's say sinusoidal position was 0, 1, 2. I would basically encode them in basically encode these directly in RY. Okay, this would be my first layer. Now I would add another layer of rotation gates where wherever Ry of x1 was there, I would add R, Z or any other rotation gates with 0 as my theta. Then for x2, I would add R, Z or any rotation gate with 1 as my rotation or my angle. Similarly goes for 3 as like that. But this is very much, you can say, big. But instead of that, you need to use very small angles like 0.01 or 0.02 or very much smaller angle 0.001, kind of that angle, so that some part of it is rotated. There is no too much rotation which would like lose your actual data. Because whenever you are encoding classical into quantum, if your angle is very different, okay, so your encoded information can be wrong as well. So to ensure that it is right, you use very small angle for rotation. Or you change the connectivity pattern or the gate order based on the position. Basically saying if I have token is first token is there, I would encode it into first qubit. If second token is there, I would encode it into second qubit, like that. Or you would have gate orders based on the positions, which we would see. So pros are embed position information at the quantum level, which might give richer interactions in the quantum feature space. But the cons are circuit becomes much more complex and harder to analyze and needs careful design to avoid an unnecessary depth or parameter explosion. Classical way, as I have already told you, basically imagine each token is a student and you want to send them into the quantum classroom or the PQC. Now each student already has a name tag. Okay, what is the token embedding? Meaning the word, patch or time step. Before entering the classroom, you give them a seat number or the sticker on the same tag. Basically, you say if this word comes out, it already has its own meaning. Okay, basically the token embedding. Now I would give it, let's say, position 1 and then make it sit on the first row, on the first bench of the first row. Then next comes up first row, second bench. Like that, I would seat them. In that analogy, you can think of this in the same way. Basically, in mathematical term, you take the token embedding, whatever is the token embedding for position I, and you get the position embedding as well. Okay, and then you form, either you sum them. Okay, so these two are going to be in the same dimension, so they can be directly summed, or you can have EI. Okay, let's say EI is 3, so 1 to 3. Then after that PI, so from 4 to 6 would be PI. So first third of your actual total ZI, or the, what can I say, total encoded information, the first 3 would be your position, or the first N would be your token embedding, and the last or the other N would be your positional vector. This is one of the ways to do it. And then you directly encode ZI into qubits via angular amplitude encode. So the quantum circuit is unchanged. Only the numbers fed into it already contain the position. Now, what if you do not want? What if you want to do it inside the quantum circuit? Again, think of students entering the classroom. They all wear only a name tag. They sit in the rows. Okay, sit wherever they are. But you do not print the seat number on the tag. Instead, the teacher changes how they teach each seat. Basically, think row 1 is there. Okay, now I would slowly tilt them in such a way that they are facing me and they are facing each other as well. And row 2 might get a bigger twist, basically creating a circle. Okay, so that each student can talk to each other and I can teach them as well. In that analogy, the position would be encoded by the quantum circuit itself. So position is not written on the tag or on the embedding. It is baked into the how quantum gates act on that information or the qubit. So variant A, as I had already told you, basically one layer would act as your embedding. These X1, X2, and X3 are nothing but your token. So whatever is your token X1, you would directly encode it here. X2 would be here and X3 would be here. This second layer would have the positional encoded of your X1. So here is X1 encoded. Now the second layer would have the rotations depending on the learned sinusoidal function of I. So basically this encodes your information and then this encodes your positional information. And this layer, this quantum state here for this Q1 would be your encoded token as well as its encoded positional information. This is one of the variation. The second variation is basically you encode position not as extra angle but as how circuit is wired. Basically qubit index token would be one would be given as in qubit 1, token 2 on qubit 2 and so on. And entangling gate would be applied to neighboring qubits, for example qubit 1 with qubit 2, qubit 2 with qubit 3. Basically this, you would have an encoding, you would have encoding here, and then this would be, let's say, token 1, this is token 2, this is token 3, this is token 4, and token 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. This is how qubit index would work. And then you would have separate positional register. You use a set of qubits that store the position for the token, basically like this. So you would have 1 0 1 0, and here you would encode the second token, and then according to the values of this, the rotation would happen, and your token as well as the position embedding would be created. And then you have graph or topology based. Basically you connect each of them, here you encode and you connect them in a graph way. Basically either this is connected to this or this connected to everything. So these are the three, not even three ways of variant B. Then you have hybrid attention heads. Classical front end can be there, quantum block can be there. So basically classical front end, you use small classical embedding layer. Then quantum QKV block would be there for each token, encode and embed into a small PQC and measure the expectations. Classical attention and feed forward would be there, compute the attention scores. And value aggregation classically, use classical MLP for feed forward. Benefits is it is much more easy to integrate, and quantum components are localized and inspectable for ablation studies. Basically, whatever the values are coming from here, you can still inspect them. But risk is over parameterized PQCs would lead to barren plateaus, which is one of the most, what can you say, bad thing about quantum ML. And unstable training would be there. You need careful comparison with equally small classical MLP to claim any advantage. So this was quantum transforms. Now I know this is very much confusing and everything, but basically think wherever I can use quantum, like in the QKV, I would replace them with replace the weights with quantum circuits. So your whole transformer is not being changed, only some part of it is changed and rest of it is still classical. So these were some of the ways you can have quantum transformer models. Now let's see how you can have quantum federated learning. This is also very much simpler way. You have classical federated learning where clients train local models on private data and server aggregates parameters using a federated average without seeing the raw data. This is very much different from distributed training. Federated learning basically happens where you have one server which has a one global model, and that global model is then given to the clients. Basically, you can think of clients as either IoT devices, or if real world examples, you can think of healthcare or hospitals where data is very much sensitive and cannot be shared with other even with the server itself or other hospitals. So how do you have that? How do you ensure that all the data is still trained to get models which can be used to predict or classify different types of diseases? Like let's say one is for cancer and non-cancer, one is for pneumonia and not pneumonia. Okay, these two data sets are there in two different hospitals. So they would train on the global model given and only give the gradients. Whatever they have trained, they would get their gradients, and that gradient is then passed to the server, which would be aggregated via average, federated average, or federated max, any way that you want to aggregate them. Now, what changes in quantum federated learning is the models are now quantum models, or you can have the communication in quantum channel. Basically, if you have, let's say, a global model, the server gives you the global model to different clients. Now, the thing would be wherever the gradients are going to be calculated, that qubits are going to be connected with the qubits of the server. And from there, you would get the gradient. The server would not look on the data, but on the gradients. Or the other way is quantum models. They just use quantum models and give the gradient directly to the quantum to the server. Basically, a global model is there. You would send the model to local quantum computers or any classical computers as well, where you can use simulators to for quantum computation. You initialize the parameter. This initial parameter would be given by the the server itself. Then each client would train locally on their data and then would give you the parameters. From theta, they would give you the theta plus 1. And this theta plus 1 from all of the clients would be given sent to the server where it would be aggregated and the global model would be trained. So drivers are basically sensitive or geographically distributed data like healthcare or IoT combined with emerging quantum resources, but need to explore the distributed quantum training without centralizing either data or quantum workloads. Where you do not want to centralize your data or the quantum workloads in one server, you can use quantum federated learning. So plain classical federated learning in one picture is basically you have a central server which would give out a global model to each of the clients. They would train locally on their own data, on private data, and the updated model would be given. Just a second. Updated model with the parameters. Only the parameters or the gradients would be given to the server where it would be aggregated, and that would train the global model. There is only one central server and many clients, can be phones, hospital, banks, labs, etc. Each client has its own private data set. Training happens would be in rounds. Basically, the thing is when this gives a global model, it starts the round 0. Here training would happen. You would get the updated gradients. It would come here. That this whole thing would be one round. And this goes on for many number of rounds till the global model has been optimized. Each client would train locally for a few epochs, then send back the updated model or the gradients. Server would aggregate them and repeat the until convergence happens. So federated learning is shared model but separate data as compared to distributed data learning, where you have shared model and shared data as well. So federated learning is different from distributed learning. So what changes in quantum federated learning? Basic idea is quantum federated learning is federated learning plus sorry, quantum machine learning. Each client now trains a quantum model. Okay, it would train any quantum model, which is the global model, instead of or in addition to classical neural network. You may have hybrid models, you may have pure quantum models as well. And clients still keep their local data, often like classical data or like images, genomics, time series data, which are very much sensitive to the organizations. They keep their local data with themselves. They only send the classical parameters of their quantum circuits. whatever is the rotational angles back to the server. So the protocol looks like federated learning, but the local learner is quantum. So you have quantum models for each client, and all the other things remains similar to classical federated learning. Types of federated learning: pure, where every client runs a fully quantum model. Full quantum model is there. The global model is also fully quantum. And the classical code would just act as the manager for round and the communication. So the communication is still classical, the round management is still classical, but the models itself are quantum. This is conceptually clean and good for scenarios where you want to really test the quantum models. Example is FedQNN framework by Inan et al., where the clients train quantum neural networks on genomics and healthcare datasets and achieves greater than 86% accuracy on 3 different datasets. Then you have hybrid, where the models are hybrid. Instead of pure quantum neural network or pure quantum CNN, you have hybrid quantum CNN, where some part of your CNN is classical, some part of it is quantum, or in the case of classical model, some part of it is classical and some part of it is quantum in your model itself. Example, classical CNN would have quantum convolution block and a classical dense classifier. So you have quantum convolution, which is connected to a classical classifier. The federated learning doesn't change. The server just sees one big parameter vector to average it out. It is much easier on NISC devices, current devices. PQCs would be small because if you're training pure quantum circuits, okay, so the number of qubits would be greater, the number of gates would be greater as compared to this hybrid model where most of the work may be done by classical or most of the work can be done by quantum and the rest is done by classical. Heavy lifting would be done by classical still. Example is federated convolutional neural network, FedQCNN, on COVID-19 and MedNACE dataset. This you can find it out here. Healthcare institutions share a hybrid CNN plus quantum convolution. The paper reports that this QFL model can outperform a purely classical baseline on non-IID splits. Basically, data split that is done non-IID way. This QFL model can outperform that. Step-by-step training loop is very simple. Assume all clients would use the same architecture of whatever is your model of the server, same number of qubits, same ansats, everything would be same. Each client has the same amount of data. For simplicity, we would say each client has same amount of data so that whatever the parameter updates come, they come at the same time. And we use a standard FL aggregator such as Fed average. Fed average is nothing but federated average. Whatever the gradients come, I would take the average. Round zero setup, you define it, you use any libraries to define a small PQC. Okay, like angle encoding plus 2 layers of entangling. Then initialize the global parameters. You initialize what the global parameters are going to be, like the circuit angles and the classical weights. The server would store these as global parameter vector, distribute them, split the dataset into k equally disjoint chunks. Distribution is there for when you want to like basically simulate that. But you can use the same data for different clients as well. Like MNIST data, you need not like split them in for different clients. You can just give the same data set. This one is basically for simulation if you want to run it. And then for each k client, load the global parameters into the models, train locally for any number of epochs. You encode the circuit, you run, measure expectation, you compute the loss, and then you use the gradient descent to update the circuit angles. And this gradient descent is also used to train the QNN locally as well as is sent to the server where the updated parameters after local training, the client would give you the parameters and then these are sent back to the server and then server would perform federated average or weighted average. Okay, if sizes would differ, if some has much more greater amount of data set as compared to some other, you can use weighted average as well. Then server would log the rounds, global loss, accuracy, whatever metrics you want to use for servers as well as for clients. Possible circuit metrics would be depth, number of 2-qubit gates, communication metrics can be there. And then you repeat until you reach a stopping condition. So what exactly is quantum? In this loop, three things are quantum. The local model architectures are quantum. Each client would use a QNN. Local training step is quantum. Gradient computation, because we are using quantum models, we need to use quantum gradient computation like parameter shift or any other quantum aware gradient rules. Okay. And parameter semantics. The parameter vector which server would aggregate is also quantum because those contain the circuit angles for the rotation gates. And aggregating parameters means combining different clients' preferred rotations into one shared configuration. Real world examples are, these are the two real world examples that you can go ahead and read about quantum federated learning. Basically, these are two different frameworks. FedQCNN, which is the hybrid version of it, which was conceived by Bhatia et al. And it proposes a federated convolutional neural network where hospital trains local quantum CNNs on COVID-19 and MedNACE datasets and only share the model parameters. And this showed that federated QCNNs can work on non-IID datasets and achieve performance comparable to the classical one. And FedQNN, where it is the QNN is pure QNN, where you introduce a FedQNN where QFL framework where clients train QNNs which are pure on genomics and healthcare datasets where it achieved accuracy greater than 86% on 3 different datasets. Hardware immaturity and simulation only reality. What is the actual reality? Most of the QFL work is still in simulators, not on actual or real QPUs. Why? Because the thing is, each client has to train your quantum model on simulators, but if it trains on actual quantum computers, there are a lot of different things that come into picture. It has to be hardware agnostic. Your each qubit cannot talk to each other qubit because in actual quantum hardwares, not each qubit is connected to other qubit. Then you have waiting periods as well. You are not the only one that is going to use the quantum hardwares. Other people are there. So that waiting time also comes into picture. Then the other thing is the cost. Now you are using federated learning in actual real QPUs. So the thing is, each and every client has to send the data, has to send the quantum circuits to the real QPUs, which may take, let's say, 1 or 2 seconds to run. Now the thing is, IBM only gives you, like, let's say, for example, IBM only gives you 10 minutes per month free. Okay. So if your machine, if your model in total takes more than 10 minutes per month to actually train, okay, not the whole, but the quantum circuits itself, all the what can I say, all the quantum circuits that are going to be there for each iteration, they take more than 10 minutes to train. So you would have to pay them $94 per minute, more than $100, with $94 excluding tax, so more than $100 per minute to train on actual QPUs, which is very much costly. Thus, most of the QFL work is in simulators only. The architect, okay. Practical drawback is any claimed benefit is under ideal assumptions because simulators are very much ideal. They are not actual QPUs. And you cannot assume it would hold on today's noisy devices. Then you have barren plateaus. Okay. Thing is, with the introduction of quantum computers, now you have barren plateaus as well, where your gradients won't be training. Okay, so Quayos survey identifies the barren plateaus as one of the two primary challenges specific to quantum effect. Barron plateau is not just specific to QFL, it is specific to quantum ML. And Ballister also notes that very few QFL papers even mention this. So Barron plateaus are also always going to be there. And many more general ansatz without
स्वतःची बौद्धिक प्रगती नाही, आध्यात्मिक प्रगती नाही, काय नाही.
So the effect is gradients would vanish, training would stall, and the federated average near random update in case of barren plateaus. Then you have quantum noise heterogeneity. Now the thing is, noise is also there. Apart from barren plateau, each and every gate that you introduces noise. In actual in simulators there would be no noise, but in actual quantum hardware, introduction of each and every gate, whether it is rotation gate, Hadamard gate, any type of gate, introduces noise. So you cannot have quantum circuits that are very much deep. Each layer would introduce a lot more noise, and you would have very less, you would have much more gradient vanishing in that as well. So the effect is some clients would send very noisy updates that can drag the global model away from a good solution. For example, if one of the client is using noisy quantum hardware, others are using simulators. So that noisy quantum hardware, that client's noisy quantum hardware would shift the gradient from a global optima to a local optima, which is very not good for quantum federated learning. Communication system. Basically, quantum communication protocols exist, but they exist in paper. Okay, many quantum federated would require either you can use quantum key distribution or entanglement distribution or even quantum secure direct communication, but it is still very theoretical. And basically the effect is a lot of proposed QFL security or communication enhancements are not deployable outside small lab test beds. You cannot deploy them on real world applications, but you can deploy them on ideal lab environments. And handling many participants and a massive data set is even very much harder. Now the thing comes up, you are going to train them. Now the thing is, all those gradients are going to come back, and that itself is going to increase the load on the server as well. With each increase in client, it's going to increase the load on the server. Thus, these are some of the what can you say drawbacks of quantum federated learning. So basically, a small, if I think, yeah, I have 5 minutes, so I'll just quickly go through the real world applications of quantum machine learning that are right now. So QML can be used to explore quantum native science problems, that is ground state energy. For example, in quantum chemistry, when you want to identify the ground state energy of a molecule, in chemistry to create drugs, create new drugs as well. If you have a very complex molecule, you can use quantum ML or VQE to find out the ground state energy. Classical ML tasks with quantum components, basically quantum enhanced machine learning, where you have small to medium data set or low resolution images. Hybrid deep learning style, where the model itself is hybrid. Okay, compared to here, the model itself is hybrid. You have some part quantum, some part classical, like just as I told you, CNN or transformers quantum generative models. Then you can have it in optimization and finance as well. Portfolio optimization, you can use QML in portfolio optimization, risk analysis, or any other combinatorial problems where you have Pareto problems, where you want to optimize two or more than two parameters in such a way that it gives you the optimum solution. So basically you choose a data set, any classical baseline, start from very small, very well understood data sets, toy data sets, medical MNIST data sets, and not ImageNet scale because those are very much big. MNIST images are still very few. Implement strong classical baselines, any linear model, SVM, small multi-layer perceptron, small CNN, tailored to the same feature dimension. You fix the evaluation metrics, accuracy, F1, ROC, any metrics. This is how you can use it for research base as well or for deploying as well. Okay, this baseline is mandatory to avoid overclaiming any advantage if you are going for any research-based applications in quantum ML. Pick the right stack as well. PennyLane is cross-platform, tightly integrated with PyTorch. Idea is when you want to have custom ansatz, complex hybrid models. So PennyLane is a very good way. QSkit machine learning is also very good, where it gives you pre-built quantum kernels, VQC, variational quantum classifiers, QNN classes, and sklearn compatible classifiers. So if you want to do very basic like quantum support vector machine, quantum support vector classifier regression, you can use quantum machine learning library. And it is very, because it is based on QSkit, it is very basic, native to IBM. So you can directly run that on IBM hardware as well. And encoding schemes, choose feature maps for quantum kernels or inputs. Basically, what type of encoding schemes you want, angle encoding, amplitude encoding, depending on that, as well as the ansatz, your actual quantum circuit where the training would happen. So you have to decide that very carefully so that it is very much expressible. It can generalize your problem very well, and it is very much trainable. So it is not very big circuit that takes very much time, a lot of time to train, but a small compact circuit with very much good expressivity so that it can be trained and it can generalize your outputs very much. And then these are the strengths, and in for each of the tools, strength in research, because PennyLane is much more used in QML as compared to QSkit ML. You can use PennyLane as well. And here are the references. So this brings us to the end of this session. I know this is a very confusing session because the thing is these what can you say, models, quantum federated learning or even quantum transformer models are not very fixed. Okay, it is not that this is the thing. You can change accordingly. You can change whatever you want. Like let's say qubit index position. Now you can change it accordingly. Okay, you can change the quantum circuit itself, which would give you different results based on whatever model you are using. So quantum machine learning, because it is in a very, you can say, baby stage or infant stage, you can do research on it. You can have researchers even in medical, even in portfolio optimization, anywhere, wherever quantum can be replaced or wherever weights and biases can be replaced with quantum circuits, you can go ahead and do your research in that. There is no fixed thing right now. Just ensure that whatever circuit that you are trying to create or whatever problem that you are trying to solve can be done with quantum circuit, with very small quantum circuits, and can be compared with classical baselines so that you have you can show quantum superiority, or it can be comparable as well. So with this, I end my session and I hand over the stage to uh, I hand over the mic to the host.
Okay, thank you, sir. Participant, if you have any queries, you can raise your queries so that sir can answer your doubts.
I think there is one. Vishwan has said, can you help suggest some references to do the research? Yeah, these references are also there. Okay, the papers that are here. These are references for quantum federated learning and quantum transformers. But if you want for quantum CNN or everything, I do have PPTs for that. Let me show it to you. Okay. So these are all the other references. For example, you want to go in quantum recurrent neural network, you want to do research in quantum LSTM or quantum CNN. These are all the references. I'll go one by one to this. So you can either take a screenshot or you can write them down if it is possible. So if you see this part, this is one of the very good papers for quantum convolution neural network. This is quantum convolution network in a different way. So if you see, there is no one fixed way to do quantum ML research. Okay. Okay. Any other doubts you have or any other queries you have?
Sir, I have one query.
Sure,
Can
sure,
I ask?
sure, sure,
Sir,
sure.
sir, actually, this transformer itself very complicated.
Yes.
So, like, if I'll use this quantum in that, right? So, what about the complication part, like the complexity part? No
See,
doubt, like, we'll have another benefits.
so okay, we would have benefits as well. There is no doubt about that because the thing is, with introduction of quantum circuits, you would have increased dimensional capacity. But the thing comes up now. The thing is, you are transferring from classical to quantum. There is one bottleneck there. Okay, this bottleneck is that basically you have to convert your classical data into quantum data. Then only it would be able to properly give you the results. Then next thing comes up, the circuit design itself. Now if the circuit design is very poor or if your encoding scheme is very poor, your data won't be you won't be able to properly, what can I say, train your data. So the complexity is much more as compared to classical. No doubt there is benefits as well, but complexity also increases. The thing is, these hybrid models, what I have shown you, they take classical and they take quantum and try to merge them. So this increases the complexity. But if you do it for very simple models, there is no complexity there. It's just the thing, if you create a very simple model, you can try to understand it. And when you understand it, you would see that the complexity is not too much. The only complexity is from transferring from quantum to classical. That is the most complex thing, because the thing is, gradients from here has to be transferred to the classical part, and then the updated parameters are to be passed to the quantum part. So this quantum to classical IO is still very complex, but it is still doable.
Okay, sir. Got it, sir. Thank you so much. Thank you, sir.
Any other doubts?
Okay, participant, if we don't have any doubt, let me conclude the session. On behalf of the organizing committee, I extend my sincere and heartfelt thanks to Mr. Sachin Namdev for delivering such an insightful and thought-provoking session on the topic quantum transformer and quantum federated learning. The session brilliantly explained the complex quantum concept with clarity and depth, helping us to understand the emerging role of quantum intelligence in the next generation machine learning framework. Sir discussed the fundamental concept of transformer, including the key terms such as tokens, queries, keys, values, and attention weight, explaining their roles in self-attention mechanism. He elaborated on the need of transformers in quantum machine learning, highlighting their benefits along with the constraints and challenges involved in quantum implementation. He detailed about the comparison between the classic self-attention and quantum self-attention, along with the insights into the large language models and their relevance in the quantum context. Sir explains the QKV mapping using PQC and explains how fidelity can be measured using the swap test. He further discussed the concept of the global attention and acceleration techniques and various strategies for implementing quantum self-attention. Also discussed classical position encoding and quantum encoding. Sir provides an insightful overview of quantum federated learning, explaining how its core principle and how it extends the classical federated learning into the quantum domain. He highlighted the need of QFL in scenarios where the data privacy, security, and distributed quantum computing are critical. He also given us the real-world application of QML and the various tools available. The blend of theoretical fundamentals, practical insights, and the further research directions has truly enriched our knowledge and inspired us to explore this cutting-edge domain further. We are grateful for your time, dedication, and willingness to share your expertise with us. Your engaging presentation and interactive discussion made the session highly informative and impactful. I would also like to thank all the participants for their enthusiastic participation and thoughtful questions, which added a great value to the session. My sincere thanks go to the coordinators, organizing team for their continuous efforts in ensuring the smooth conduct of all the sessions. Once again, thank you all for being the part of this enriching session. Thank you and have a wonderful day.
Very quickly, I'll just share my contact details. And this is my email, my personal email and my work email, as well as my phone number. So if you have any doubts or if you want to learn more, you can contact me via email or via phone. So I hope you have written it down. Thank you. And
I request. Yes, sir.
Thank you,
please
sir.
take
Thanks a lot.
Thank you. No problem. No problem.
And
Thank you
thank
for
you, Sachin,
inviting me.
sir. Yes, sir, because we contacted you very end moment, so Naresh sir helped me to coordinate with you. So thank you so much, sir. And you have enriched our FDP, sir, with the practical and the theoretical blend. Thank you so much.
Thank you. Thank you. Thank you for inviting me. I
Yeah.
hope everybody has learned a lot, and in future they also try to learn a lot, because this quantum ML, even for very big like quantum transformer and everything, is very much confusing. But do not worry, I'll be here. I am here to clear up any doubt that you have. Okay. With that, I hand over to ma'am.
I request everyone to please turn on your camera so that we can have one photo. Thank you all. Thank you, Sachin sir.
Thank you. Thank you. Thank you for inviting me.
Hello. Hello, Dr. Shravani.
Hello, ma'am.
Hello, how are you?
I'm good. I'm good after a long time, it looks like.
Okay, I welcome you.
Thank
Thanks
you,
a
ma'am.
lot for
Thank you so
joining
much.
this.
Thank you so much, ma'am.
Okay, so I am Dr. Amrita Ruperi, coordinator of this course. I welcome you, madam, on behalf of the Electronics and Telecommunication Engineering Department of Vidyavardhani's College of Engineering and Technology. I invite Sandhya Supalkar, madam, to take over the session. Sandhya, madam.
Yes, ma'am.
Good afternoon, all the participants. Today, I welcome you all again in this AICT sponsored ATAL Faculty Development Program on quantum intelligence, exploring the convergence of quantum computing and artificial intelligence. Friends, today we have on this second session, for the second session on day 6, Dr. Shravani with us as a speaker. And before we start with the session, I would like to brief you a versatile profile of Dr. Shravani. Actually, Dr. Shravani already conducted one program in STTP, and she conducted a lecture on this quantum computing, and that encouraged us to once again listen from her on quantum computing. So before I would like to start with the session, I would like to brief you about Dr. Shravani. Dr. Shravani, she is an associate director at Deloitte, where she leads the quantum safe cybersecurity, cryptography, and quantum computing practice within the emerging technologies cyber division. With over 20 years of experience in cybersecurity industry, she brings deep expertise in cryptography, data security, quantum cryptography, and post quantum cryptography, and holds 2 patents in cryptography. As a strategic technology leader, Dr. Shravani has worked with leading organizations across finance, defense, healthcare, and education, delivering robust cryptographic solutions that stay ahead of emerging quantum era challenges. She is recognized thought leader contributing to research publications and public speaking on topics at the intersection of cybersecurity and quantum. After knowing about his versatile profile, we are really eager to hear you, ma'am. I welcome you in this ATAL FDP, and I request you to please start with the session.
Thank you so much for this kind introduction and inviting me for this ATAL FDP. I had visited, I think, 1.5 years back to your college, and Sunaina is one of my best friend. We were with VGTI together, and I enjoyed that session and hope to have a same on this online. I don't prefer online. I have my own reservation about it. I prefer to have a physical connect with the participants. Uh, I have my own reasons. Of course, online session gives us an opportunity to connect the participants across globe. But after COVID and when I sat at home, I realized that physical connect gives you more connectivity with the participant and the subject. But thank you so much. And I would like to take you to the journey from the other lens, because I was going through your FDP program, and it's heavily loaded with a lot of great experts across the globe on a quantum computing and the cryptography side. Um, and this is one of the emerging areas. I would like to say there are a lot of myths around quantum computing and cryptography, that this is yet to come, and we still, exploring. We don't have quantum computer where we can conduct the experiments. To some extent, I would like to clarify, but the lens of this complete webinar will be through the cybersecurity. I'm being in cybersecurity expert. So can I get the sharing rights? I have a sharing rights.
Yes, ma'am, you can share it now.
Okay. Let me know if you can see the screen. I'm not sure if you can.
Yes, visible.
Okay, cool. So This is actually a wave that you can say in the industry nowadays, and it's every day when I am going through the various posts that is getting posted on the LinkedIn. Since I think 3 years, I'm extensively following this quantum safe cybersecurity. First of all, I'm a crypt analyst. I break ciphers. So I enjoyed my PhD with Professor Virendra Sure at IIT Bombay. We were trying to break the ciphers like RSA, stream ciphers like bivium, trivium, and gift. Lot of, I mean. And while performing that experiment, I realized that it's the toughest field because these ciphers are made by the expert across the world, and they are used in our digital communication or digital ecosystem. And it's always a pleasure for a crypto analyst once they are getting the break. When I started my PhD, actually it was in image cryptography. I am also an image processing machine learning expert. So, professor asked me to continue with this image cryptography. But while during my academic journey, when I was at one of the Mumbai colleges of the Mumbai University as a assistant professor, I started learning this subject on encryption, and it's landed up as nobody was there to teach, and I'm an electronics and telecom engineer, expert in statistics and probability. I always like to work around the data compression. So it was a combination of data compression and encryption, and it was like nobody is there this semester, you please take this subject. Mm, I said, I can take the first part because that, attracts me. It's being statistics and probability, data compression. But what is this second? I don't know because it's was hardly read by me that time. I think 2010. I was not that internet savvy, and still I am not that. But I prefer to read books. I never came across. I was into digital communication and understanding encoding, decoding part. Error correction was my passion. And I started reading this subject. I realized it has a magical qualities. And I started learning more and more about the number theory and abstract mathematics, which was never learned during my graduation or post graduation. And I enjoyed sitting, learning, understanding the magic. Got into this and then realized that I have to do my further education or PhD in this subject. I landed up through various experts, but I could able to find only one, which is at IIT Bombay, Professor Virendra Sore, who is a cryptanalyst. I mean, I'm very proud to say that is now only one of the who works in algebraic cryptanalysis. Convincing him was a toughest job for me. Somehow he managed, and thanks to my professor at VGTI, Professor Daruwala, he allowed me to do this joint work with IIT Bombay. We could able to break the ciphers with the same enthusiasm. I wanted to pursue postdoctoral study in the same. COVID hit. I had no option but to sit at home, and then I started exploring industry, where exactly ciphers has been used, what exactly the, and I applied in various industries. I got through once uh, uh, at DACI. DACI is NASSCOM's body, who is a industry body. Not directly work into the field, but they do a lot of policy work, a lot of webinars, awareness session. And I became the part of it. I got the exposure to the industry and then started understanding the perspective of cryptography from the cyber. Cyber was that time not that heard by me. I was like, okay, there is something called cybersecurity. And I always inclined towards computer networks, which was one of my favorite subject during my bachelor studies. Uh, and then I was trying to understand from CCNA, NP, the network professional, network administrator, and all. When I started DSCI, I realized it's a whole new world that cybersecurity has, where people consider cryptography is one of the controls, is the correct word if I would like to put in front of you. And I started reading more about it. I started organizing more webinars around cryptography, cryptographers all across India, to give a perspective from the cyber. 2021, I had come across this quantum safe and quantum threat. We organized one webinar on a quantum safe, through which we invited Professor Michele Mosca. And that was the first time I got introduced to this gentleman, who is a pioneer in quantum safe and cybersecurity. He is also an cryptanalyst who extensively worked in, now also he is very active, and he is one of the uh, scientist turned industry expert, who advise whole world how this migration has to happen. And then I picked up into this area, worked into various organizations, and currently I started, I mean, it's almost more than 2 years now. I'm leading this efforts on quantum safe cybersecurity at Deloitte. Deloitte, being Deloitte, is one of the wonderful companies. They always supported me. My leaders are very good and supportive. They allowed me to pursue this because industry always look into the lenses. What is the business value? When I started this journey, there were only the awareness sessions I could able to, and some of the POCs, and people were having lot of questions around whether the quantum will really going to be a part of the mainstream or it will remain into the research for more than 20 years now. So this session is not about quantum computing directly, but what quantum computing to the cyber world and how it is bringing the threat to the cyber world. So before jumping on to the actual topic of quantum safe cybersecurity, just a brief. Many of you might have heard about today's classical cryptography, which is actually a backbone to the digital ecosystem. I would just walk through and then try to connect the dots with the cybersecurity, and then position this complete talk from the cyber perspective. Uh, as I mentioned, the cryptography is a backbone to the digital ecosystem. Whatever we do today, right? Be it entertainment, be it now we are doing this educational webinars, healthcare industry, manufacturing industry. Um, Everything is undergoing in from the physical to digital transformation perspective. Reason being, we wanted to have so many things. First of all, automation is one of the things. Second, we wanted to have the remote connectivity. We wanted to make the ease in the operation. And with AI coming into the picture, we wanted to do a lot of analytics so that it can beneficial to the businesses, to the society, to the healthcare industry, to the educational industry. And this transformation picked up long back, but if you see now with the AI, it is picking up heavily. Uh, Everybody wants to bring new flavor to whatever processes, applications that we are developing through the AI. And for that, we need a data into digital form, right? So, and this is how the digital transformation has picked up rapidly, and transformation started happening. Thanks to your LLM, I'm not that far for AI. I have my own reservations. I follow Jeffrey, and I understand the threat that is bringing to our society along with the benefits. Same goes to the quantum. I'm fan of quantum with for a different reason, but what it is bringing to our world is a great threat. We'll see it into the upcoming slides. Uh, so when this is picking up, the data what we are using. I would like to give example here that COVID hit and we had no option but to sit at home. We cannot put our important assignment, our education on hold. 1 or 2 months was quite okay, but we started giving whole things uh, online. And then we were so happily started using VPN. Considering that VPN is the most secure communication channel where our data will never get accessed or hacked by the uh, hackers or the person who's supposed not to see my contents. This whole digital ecosystem, cybersecurity, is because of the cryptography, which is extremely niche. I would like to say, put here, it is like a spine to our digital cyber ecosystem. We cannot see it, but without it, we will definitely fail. And then crypto has two parts. One is cryptography, where we are encoding the contents, converting entire text into different forms, which is non-readable to the non-intended or unintended party, and it can be only readable by the intended user. And another version of it is breaking and cryptography. Uh, it's a mathematics where the many cryptographer that those who are siloedly working as a mathematicians, uh, bringing this beautiful algorithm to the world so that we can safeguard. What are the different goals that crypto is actually serving? If you see, cybersecurity has main purpose. First is whatever data is flowing through your digital channel across the insecure media, that is internet, has to be secure. It should not be known to unintended. So confidentiality is first goal that cybersecurity is always looking forward, and which is actually accomplished by cryptography. There are two aspects. One is when I am inside the premises, like I'm inside the house or I'm inside the organization, I am taking utmost care that I'm transferring a data by using LAN. Maybe I'll not consider to that extent that I have to use the cryptography. So physical security is paramount. We have to consider that. Again, there is one more factor that we always have to see is the trust. When I'm generating keys, when I'm transferring keys, the trust is the major factor. But apart from that, when I'm taking care of this too, and my data is encrypted using cryptography and traveling to the internet, insecure media, crypto is the one who is taking care of everything. That is confidentiality. Second very important thing is that the authentication, me being and me, when I am authenticating website, I'm accessing a website, I'm accessing a data from the server. I have to authenticate myself that I am Dr. Shamni and I am authorized to, access the content. So that role also can be fulfilled by cryptography, and that is the another type of cryptography, which is called as the asymmetric cryptography. Uh, Entire thing of crypto is based on two. One is the algorithm, another one is the key. Uh, an algorithm is known to everyone. What we need to secure is the tiniest element, that is the key. And exchanging the key is a very big task when it is coming to internet. Now I'll share some of these stories around, how cryptography, symmetric cryptography, and birth of asymmetric cryptography has happened because of the limitations in cryptography. But secure key exchange is one of the goals that crypto is also fulfilling. While we are having this digital world, e-commerce industry, we are doing a lot of online transactions, and non-repudiation is another very, very important quality. I mean, I am placing an order. I should not be declining it later, right? Or the order is getting confirmed by the manufacturer. Once I pay, it should not be declined. That complete role has been taken care by crypto, which is called as the non-repudiation. This is all about 4 goals. There is one more goal which is very important. When I am transferring the data, it should not get changed. And if at all it is get changed, I should be knowing about it. And that role also has been fulfilled by cryptography, which is called as the hashing. This is the integrity. Very best example is that I am doing any interaction, financial transactions. Um, I would definitely like that if I'm spending 100 rupees, 100 rupees has to be deducted from my account and not the 1,000 rupees. And bank would definitely like to see it's 100 and not the 10, right? So integrity is the very major part. Uh, that is when we are doing any online transaction, not only the banking, there are a lot of other places. We can say that the trade secret when we are signing in contract, right? So we don't want anybody to change our content, and if at all there is a change, it should be captured. And this is also beautifully done by cryptography, by hashing functions. So for me, crypto is a magic, which is actually doing a lot of things. And code breaking, I'm a cryptanalyst. So code breaker, although code making is a science in mathematics, code breaking needs a variety of thinking. Although there are certain kind of formatted methods that already been given, statistical, differential, algebraic, side channel attacks and all. But again, it's an art. We have to think how we can break the cipher. Uh, this is how cryptography is backbone to the digital system. Now let's come to the one part that is public cryptography. Why it is, I'll explain you that. Uh, Give me a moment. Yeah? Okay. While explaining the cryptography, I was showing 3 types, right? So it's a symmetric key cryptography, then asymmetric key cryptography, and the hashing function, right? Symmetric cryptography, you can say it's from the ancient, right? And then what it does is it takes only one key to lock the content and to unlock the content. Mm, I can say it's one of the best form of encryption, and breaking this cryptography is extremely hard. So algorithm currently what we are using, AES, is developed in 2001, and it is still continued after 25 years, considered to be a post-quantum cryptographic algorithm. But the major challenge in this one is we are using single key, and when we are using a single key, when we wanted to give this key from sender to receiver, I mean, both should have, right? Then only they can decrypt the content that has been get locked by the sender. We have to have mechanism that was manual. We cannot share this key in the band. And this is what the major challenge that has industry faced so many years. Cryptography was used before 70s, majorly in defense, heavily in defense. For some of the banking, highly restricted area, uh, because of the limitation of the key transfer. And then the mathematician thought over it, and then the whole process of how we can do the secure key exchange in band. Means when you are in band is the internet. Can we do it? And then Diffie-Hellman, they have come up with a beautiful algorithm of key exchange, which is called as the Diffie-Hellman key exchange algorithm, where we could able to exchange the keys in the band. in insecure media. And then the birth of public key cryptography has been come, which is again the another name of asymmetric key cryptography, where we could able to achieve the goals of confidentiality, authentication, secure key exchange, and non-repudiation. Uh, this beautiful field given up the way to the cryptographers who think that we should have the mechanism uh, more robust, easily using, and not only the secure key exchange, but also to secure the another goal of cybersecurity, that is authentication and non-repudiation. Three gentlemen had come up with the beautiful algorithm which is called as the RSA. After that, the evolution happened. ECC, ECDHA, a lot of many algorithm has come, which are coming into the asymmetric key cryptography category, which is called as the public key cryptography. What it has an algorithm and two keys. One is the public key, which is available with everyone, and another one is the private key that is available only with the recipient. And this made everyone's life easy. And then this is where we started using it in around 1978. The RSA, birth of RSA has happened. And then similarly, the internet started growing. For me now, when I look into the growth of the internet is not organic, it's inorganic, widespread, right? So same time, the things started picking up on the public key infrastructure. People started using it extensively. And now if you see each and every industry, like be it banking, be it finance, be it manufacturing, be it automotive, utility, transport, even in the education, we are extensively using public key cryptography, public key infrastructure. If you see the examples, I'm trying to put from the banking and finance perspective, but you can actually take any example, pick it, and you will see that this public key infrastructure has been used extensively even in manufacturing and automotive. So one is the payment system, Google Pay, what we do, right? Wallets, customer authentication, then net banking, I mean, demat account, a lot of things. ATMs transactions, VPN connections, our Aadhaar card, everything is linked with this. And it is beautifully developed algorithm which ruled the world, entire world. I mean, till today, I still remember in 2013, I had done one survey on public key cryptography, RSA. And I was amazed knowing that there is a more than 30 years of attack that is going on RSA, and people couldn't break it. And it is based on beautiful concept, which is called as the fractorization. We'll see that later. Now, if I would like to put you through the organizational perspective, how it is used into the systems, right? If you see any organization, this is what the normal functions are. We have the organization where you will find that multi-services, legacy systems, then there are firewalls. This is typically the IT infrastructure. And nowadays, I cannot say it's IT. Even OT is somehow, using IT infrastructure extensively. But you will find that employees are sitting inside the premises. They're having their own devices. Then there is logging requirement, then there is a server which is inside the premises, firewalls, and then there is a internal storage, which we can nowadays say as a cloud storage, right? So we are also transferring our data into the cloud, and cloud computing, cloud storage is one of the another beautiful invention, I would say, that where we can actually save. I mean, many organizations could able to save the infrastructural investments. Then our internet services, proxy, DNS, mail server, internet routers. And then it can be internal network or it can be external. And then we being a customer or the user, we are sitting outside this organization and can fetch the data. So for example, if I would like to say here, if I, just a minute. Oh, I can't minimize it, is it? Okay. Okay. Uh, for example, I wanted to use and secure communication, and I want to fetch the personal data from the server or any, want to do any transaction, transfer of the loan document. I would definitely use the secure communication, which is VPN nowadays. And then sitting outside, I'll be using secure banking websites. When I'm using it, first layer is the OSI stack. We have the application layer, and we are using the applications, various applications, web applications, whatnot. Next to that is the protocols. That is HTTP, TLS, SFTP, VPN, and IPsec. First thing I would like to put here that wherever you see S, right? HTTPS, TLS, SFTP. S is security, S is cryptography. So before few years, those who are from the cyber and IT background, you might have remembered that we were using HTTP. S was not there. And then data was flowing through the website in a plain text form, the message as it is. But then hackers, being hackers, they try to exploit it. And gathering our data, we started using HTTPS. And that S has different algorithm, which is called as the AES, RSA, ECC. You will find this algorithm everywhere across this OSI layer stack, from 7th layer till 2nd layer. Everywhere people are using it. And we have done extensive study on this. So this is how, the bigger picture, we can say, of the organization, any organization, a few parameters here and there, but you will find this is commonly used. And crypto is extensively used. Now, if you'll see anything that is going beyond the organization, we are relying on cryptography and secure protocols. Oh, from the use cases perspective, if you'll see that, there are certain use cases like data center, customer authentication, HSM. This concept you will find extensively used by regulatory bodies. That SBOM, that is software bill of material. H is hardware bill of material, and C is the cryptography bill of material. Now, when we try to see this through this lenses of software bill of material, that means we have to know each and every component that has been used in the software, and we are making an inventory of it. Similarly, it goes with the hardware bill of material, where each and every component that has been used in the hardware, there should be an inventory, and we are keeping it. When we were trying to understand this whole elements of software, hardware, routers that has been used in the organization, from the cryptography bill of material, we realized that crypto is the central part. You will find in the software, you will find even in the hardware. And this is how the first requirement as has been come from the SEBI and the CERT-IN, which are our regulatory bodies, which is watching our Indian cybersecurity postures, that we should have the inventory ready. This movement is not only in India, but it is extensively happening across the world. Reason being, there are a lot of attacks on the infrastructure application that we are using through the vendors, supply chain, how we are implementing the application, lot of things, right? So we should have, and this is what the first thing that every organization is actually looking forward. So I have a time till 5, right? Am I audible?
Yes, ma'am.
Yeah,
You
okay.
can.
Yeah. No, I'll expedite because it's already 40 minutes. So when we are talking from the classical cryptography perspective, we were very happy. I mean, I would say that we are still happy. We don't have to say that we are not happy. We are using RSA 240 2048. 2048 is the key length. AES 128 1256 SHA. And then this is extensively used for various use cases like, digital signatures, like for authentication purpose, for secure key exchange, for data encryption. And if we will try to break this, uh, it will take a time like 300 years, billions of years, infinity. People couldn't, estimate it with whatever capacity, computational capacity we have right now with the supercomputer also. And that's the reason we are so confident that we are not even considering that crypto exists, right? It is like an invisible clock or invisible shield which we have, and which is serving us to do all this uh, digital transactions securely. You will find these elements even in AI. And that is how the secure AI concept that is picking up in the industry, which is different part. I'll not go here, maybe some other time. Uh, so we are happy because we can't, this cryptography can't be broken. What will happen if it will get broken, right? And what are the different causes that maybe the cryptography failure can happen? First and very important thing is that weak cryptographic algorithm. And then one of the bodies worldwide, NIST, National Institute of Standards and Technology, USA, they have taken this whole what you say, responsibility on their shoulders since a lot of many years, and they are producing this beautiful ciphers to the community. They used to give the advisory that which cipher you should be using and which cipher you should not be using. So DS was the first algorithm which was actually used in the industry. There were attacks that had happened by crypto community and then realized that this cipher is broken. They have come up with the algorithm called as the double DS, triple DS. And this advisory was floated by NIST. People started, migrations in the industry. They have also come up with the challenge when they realized that DS is not serving the purpose. In 2000, they shortlisted one beautiful algorithm, which is called as the AES. Which has happened to be one of the best algorithms till today. And people are relying on that for the confidentiality. We are just increasing the size. Being in cryptanalysis and understanding the attacks that is happening on AES, I have a dilemma whether how much it will survive. But this is what the weak algorithm is. Once it is broken, you can actually decrypt the data. And this is how one of the cause that there can be a failure, which can lead to the risk. Another best example of failure of cryptography is key management. Why and how? There is a myth. Many times people think, oh, I'm using an algorithm AES and I'm, very much secure. It's not like that. Algorithm are publicly announced. Everybody knows the mathematical structure. What we know or what we have to keep secret is the key. And this happened because of the World War II, where entire Enigma machine was stolen and got decrypted by Alan Turing. And entire history of World War II changed, right? So Kirchhoff has come up with the principle saying that the larger piece, that is the algorithm or a machine, it can be open to the public, but the smallest piece, which is easily can be protected, is the key. But inadequate key management can lead to the failures. Weak protocols, implementation flaws, insufficient randomness, key compromise. These are the different failures of cryptography, which causes the risk that is unauthorized alteration of the data, fraudulent authentication, decrypt sensitive data, and forged signature. Means almost all, right? Anybody can read your information. Anybody can forge your signatures, digital signatures. Anybody can alter the data, and anybody can impersonate. So I'll leave to your imagination. If at all crypto fails, what will happen? What will bring the impact to it is not only the personal level, because these questions many times asked in the industry or in the forums that mera koi kya bigadega, right? So individually, how it will harmful to me. Correct. Maybe not to that extent, but if you'll see from the banking perspective, if my data is getting altered, uh, it is going to make a lot of difference. Another very best example here I would like to put is the WhatsApp security. We all often see that, end-to-end security, and we are very confidently sharing a lot of material over WhatsApp. End-to-end security is based on the RSA. And then we are confidently saying that my data is secure. Trust me, it is not anymore. Although there are certain factors which is called as the implementation flaws and libraries that has been used. I'll recommend don't use WhatsApp for communicating, sensitive information, because advisory has been published by NIST or NSA that this data is getting leaked, and the libraries those are has been used, those are not foolproof. So that is another topic but it is bringing a lot of impact to our individual lives, organizational level, and the national impact. Now, I would like to keep to your, discrete imagination that after discussing all this, we can say that the crypto is at very niche as in every digital systems, being it hardware, software, whatever we are using. It's concentrated, and these are the only algorithm that has there are certain others algorithm. I would not say there are not other algorithm, but these are primarily people are relying on, because this is security is tested well by the community. But there are certain proprietary algorithm which I don't believe they are strong enough. They have been also used, but this is called as the uber concentrated. Take any product, any protocol, any application, you will find this, and that is how which is called as the foundational level concentrated risk. There is a very big incidence that had happened, which is called as the hard bleed bug, which is because of the OpenSSL implementation flaw. It's not even the failure of the cryptography. Still, there is a lot of havoc that has happened across the industry, and the vendors or the application developers, they were not even aware that these kind of risk already exist. Uh, this is all about our crypto, our current cyber systems and digital ecosystems. And I will leave to your wild imagination how far we are now, right? How many devices we are connecting, IoT devices, how many applications we are developing every day and connecting to our internet services. We are extracting the data, computing it, developing AI applications. And we are happy about it because crypto is serving its role, right? If everything is going fine, digital communication is going fine, we are happy with digital computing, why this quantum computing and whole stuff, right? Throughout your FDP, you must have learned a lot of things, and I know that you all are researchers and faculty. I respect them a lot because their readings and understanding about the subject always to the next level. Um, why we still need quantum computing is the question, right? Can anybody would like to answer this? Yeah, anyone? Am I audible? Am I audible?
Yes, ma'am.
Yeah. Oh, okay. So,
Yes, ma'am.
am I going off track or somewhere like where you are not? Where you couldn't relate the subject. I know that it's off track, but yeah, from the quantum computing perspective.
Ma'am, as I understood, there are two reasons. One, certain tasks which are specific can't be handled by the current classical computers.
Correct.
Hence, the quantum is essential. The second part is speeding up the current computing power with the exponential increase in the data, which is also necessitating the quantum concept. These are the two
Correctly.
reasons as well.
Correctly said, sir. It's correctly said and beautifully captured. So quantum computing is the need of an hour, or you can say we need it with the correctly said examples that current computational capacity what we have is not the way cannot solve the problems which we wanted to solve, and these are the major examples: weather forecasting, correct weather forecasting, financials, telecommunication, then drug discovery, logistic, because it's a widespread, and then AI is also picking up. Of course, quantum, I will not go in detail because you already know this superposition, entanglement, and quantum interference. And there are other properties, beautiful properties, that is actually making quantum computing and this whole area or the paradigm attracted by the research community. And of course, when the research is successful, the industry adoption is widespread. And we can see that the industry adoption started happening now. So I'll not go in detail, although I would like to say beautiful example, and I'd love to put it in every seminar where I delivered, which was given by Michele Mosca, and he is my idol. I follow him. Um, so what is the need of quantum computing, he explained, and which clicked me well. Uh, we before few years we were using Earth as a square, right? And then we were doing all the the calculation around it, thinking that if we'll go far further, we will may fall down and all. At certain point, we realized that we cannot get the exact answer, even though we are taking some measurements, right? And then the question is, are we taking the wrong measurement? Are we doing the wrong computation? The answer was no, right? And then from square, the paradigm got shifted to the sphere. And we started looking into the another paradigm. We could able to solve the problems which we couldn't solve by using the square, or and this is how the same exactly things are happening in case of quantum computer, that whatever we are trying to achieve with the digital computing, it reached to the limits. We cannot solve the problems, and that's how the development had happened in about 100 years ago, uh, when people started seeing this things on a micro level. There's something different that is happening, and that is how the birth of quantum mechanics has happened, and people started observing, trying to put the theories around it, hypothesis, practical implementation, and the field grew, and we reached to the level that we could able to now say that quantum is no more an fancy theory, or it is still in the research. We can actually use it into many of our application. Maybe it's not the great way or the capacity, because of it is still evolving, but it is evolving, and it is evolving in all sectors: hardware, algorithm, sensing, material. So it is picking up. And then this whole paradigm is bringing new opportunities for us, so that we can solve certain problem which we couldn't solve. This is kind of development that we could able to capture, that how three classical cryptography, classical computer, and quantum computing is picked up. And people were saying that quantum technologies or quantum computer is 30 to 40 years away from now. And, there is a little bit slower side of adoption was going on by the industry. When I had done my research, I realized that this whole thing, private industry started investing into this, right? So I don't know whether I could able to capture that, but that there is a graph that has been given by one of the companies, leading companies, where there is a spike that had happened in the investment side from the private industries. After 2020, like COVID, one thing is very much sure that public sector government always support research. So there were fundings. People across the world, they were trying to solve this very many problems on a quantum computing. But when the private company invest in anything, right, they will always see the value to the money, ROI. What I'm going to get in return. Am I going to get in return? And that is how I could able to say that sparkle my eyes that if the private industry is heavily investing, that means they know there is an ROI, right? Uh, and this whole game of 30 years has reduced down to 10 years, and you can see the predictions how it is changing. November 4th, 2025, there was an announcement by Department of Energy, USA, saying that we should have a fault-tolerant quantum computer by 2029, which the challenge was accepted by Jay Gambetta. And he announced it publicly that, yes, we are getting funded by DoD, and I'm taking this challenge to bring the quantum computer, fault-tolerant quantum computer, into the existence. Of course, there are very many leading companies like IonQ, Microsoft, Google. They have also expedited this whole thing, and then they said that we are coming up with the fault-tolerant quantum computer by 2028. We are in 2025. We have 3 years now. That means we are getting something where we can actually do the experimentations, what you are developing in quantum and AI, right? What it is bringing to us. As it is bringing the blessings where we can actually solve a lot of the problems, it is a threat to our digital communication system. It is actually can break the ciphers. RSA, and this invention that had happened when actually we were trying to solve Y2K problem. Shore has come up with the beautiful algorithm, which is actually based on one of the Indian scientists. I hope I will not forget the name, Vajrani. And then he put up one algorithm. There were certain flaws, and Shore has corrected it. And he has come up with the algorithm where he theoretically shown that quantum computer with certain capacity will come into existence. RSA will be broken. Means factorization, which is NP hard problem, will be broken. Yes, I mean, people were not taking it seriously. People were using RSA extensively. There is another gentleman, researcher that has come up with the algorithm, which is called as the Grover's algorithm, which says that, okay, search can be reduced if quantum computer of certain capacity will come into existence. So these are some of the calculations that has been given. RSA will be broken in few hours. Of course, there are certain assumptions that has to be make that we need a quantum computer of certain capacity, right? Even AES with 128-bit keys, the range of the algorithm will be reduced. So sorry, there is anything I have to do. Now, what will happen? First and very important thing is that harvest now, decrypt later. It's the major threat that is there to our digital ecosystem. Trust now, forge later, fraudulent authentication, and unauthorized alteration of the data. All gone, right? I mean, Anybody? So this thread is going on since long. First one, harvest now, decrypt later. How it is, I'll explain with the pictorial thing. This is my bank. I am using encrypted data by using VPN channel. And now what hacker has to do? Hacker has to attack a system, get in keys, and then decrypt the data. Now they don't have to worry. They will just take the encrypted data. They will put it into the database. They will wait for the quantum computer of certain capacity to come into existence, and then they will attack it. So this is how harvest now and decrypt later. And this is one of the major threat. Similarly, they are trying to capture the signed documents, which can go for a longer time, like, and then they can forged by breaking the RSA. And this is actually bringing the lot of threat to our digital ecosystem. Not only the banking, but also the manufacturing industry, OT industry. We are using railways transport, the aerospace, space industry. If you see everywhere, maybe the structure is different for the protocols, but the underlying algorithm has to be this: RSA, ECC, Diffie-Hellman, and AES. Threat is bigger and it is growing day by day. Time is getting squeezed. So this is another example how they're capturing your digital certificates and will decrypt it later. And then it is also a threat to many applications. So I'm just leaving it to your imagination. What is the scale of the threat that we are going to deal with? There are certain factors that actually accelerated this risk, right? So one is that we are relying on one algorithm, which is called as the Shores and Gross algorithm. Trust me, crypto community is crazy, especially crypto analysts. They wanted to understand if we can find out any flaws mathematically. So this is the best known algorithm, but what is going on behind the back, nobody knows. There are, when it is crypto, I compare this situation with the war situation, because our data is flowing across, our country's data is flowing across. We are confidently, transferring the data. And it is nothing like a war zone now, right? So next war will be the cyber war. There will be less physical wars. And then cryptography, which was extensively used in the defense system, now it is used extensively in our civilians' life as well. And then, if at all, I am having the capacity to break these systems, will I publicly announce to the world, or I will just keep it to my advantage and I'll see the data that is flowing through and I'll try to decrypt the data, which is again in your imagination. That please let me know from your understanding and views that will I announce to the world that I could able to actually achieve this supremacy. So there are a lot of invention, as I said, on a hardware side, software side, material side, sensing side that has already picked up, which is actually leading to crypto-apocalypse. Meaning what? I will not only rely on quantum, but I will join hands with the supercomputer and try to bring this Q day closer as much as to my advantage. And it is leading to the risks, which is called as the entire critical infrastructure, like banking, power, your transport, manufacturing, oil and gas, all right, aviation industry, nuclear power sector will be vulnerable. We will not have a quick fix. Reason being, as I say, the internet, our digital ecosystem has grown inorganically. We many a times, if you try to see in your own organization, we don't know who is developing an app, who is plugging into the system, what data is flowing through, what hardware we are using, what application, what computer from where it is getting. Although there are a lot of mechanism and the applications, those are available where we can actually track all these things. But there are certain places where we are using legacy system where we cannot move the data. we have to, we are just oversighting. It's like, okay, it's there. We don't want to touch it because, upgradation is not possible. We have certain level of cryptographic algorithm that has been implemented. Now just imagine how much manpower we need to solve this problem. Uh, I don't think so it's the right comparison people give it, Y2K, because none of the factor is actually same, uh, except that it's across the digital ecosystem. Now, one thing I would like to put here that if at all this calamity is started envisioning, can we put a brake onto the quantum computing commercialization? We being in India, very liberal, we have a lot of empathy and sympathy. We will may go for it. Will our neighboring countries do that, right? Rather, they are expediting, and that's what the news I come across was, and which was actually shaken my world was the quantum chip has been delivered to Pakistan by China. They're helping each other, strong, powerful enemies, and we are also powerful. I mean, I'm not saying I will never say that we are not powerful. We have to be super powerful. That's what I would like to put here. And then we have such a community, a strong community, academic researchers and industry that we can actually achieve this whole transition from quantum unsafe to quantum safe. But we have to start it now, or maybe we could have started. What is happening in this one is the quantum and AI actually expediting the things, right? So how AI is expediting? AI is actually helping to find out the algorithm which will go correctly with the attacks. And in defense side also, it will help us to find out which can be used by the quantum computer to defense it. So it is like we can use it the way we want, but it's again whoever is having the access, right, on this whole quantum computing and AI systems will be using for their advantage and disadvantage for a defense and the attack side. This I have already explained. I just wanted to put here that we are reaching here. Risk is here, and then we have to solve whole this paradigm when it coming from the cyber security perspective. This is the threat timeline. I have 15 minutes, sorry. Where we will try to say that do we have to start or boil the whole ocean, right? It's a whole massive thing. So Mosca has given one beautiful algorithm many years back, which is called as the Mosca's threat line. And we have to see the transition from the data life perspective and the shelf life perspective and the hardware life perspective. If my data life is more than 10 years, for example, my personal data, right? I'll be living another 30 years. So if at all the data is transitioning or is getting travel across the network, I have to first fix it. I have to see what is the severity of the data, right? Publicly available data, we don't have to bother much. Of course, there are certain elements which is where we have to address, which is called as the integrity part. But people will try to break first RSA. So, we have to address this part of authentication and digital signature part. So this whole concept is based how slowly we can migrate by using the data life and the systems, and how we can do the transition. What are the solutions? The solutions are available, of course. NIST has done beautifully a job. They have launched this algorithms competition in 2016, and they have come up with the 3 standards, which is called as the key exchange algorithm, which can achieve by RSA. So they have given the alternative, which is called as the KM, which baseline is the KIBA. Then we have also digital signature and digital certificates. Those are available with us. So this is based on the mathematically hard problems, which is kind of one of the solutions immediately we can go for, right? Honestly speaking, it's not immediately transition for these cryptographies always takes years of time because it is embedded into the system. It is hard coded into the system. It is not, the libraries are not, compatible with the software, newly launched software. A lot of things are there. But still we have a solution. There is another set of solution that has come, which is based on the quantum mechanics, which is called as the quantum key distribution, quantum random numbers generators. And based on this, there are equipments, those are there, like quantum routers. But this will definitely need an PQC solutions. So how the migration will be? NIST has suggested that we should not be immediately transitioning from classical to post-quantum cryptography and QRNG. We have to keep our layer of RSA right now the way it is. Reason being, it's like, when we are developing a drug, right, for certain illness, it has to go through the trials. And then same goes with it. There might be an attack, adversaries can attack on a PQC and it can get broken. So we have to be, secure or confident enough that we are now completely transitioning towards the quantum, post-quantum cryptographic solutions. That is the first step, that classical layer has to be there, which will, of course, bring the overheads and the operational, efficiency impacts. Next step is the PQC and QKD, which is moving from classical to quantum safe complete solutions, and then quantum network. So there is a parallel network that has been getting established, and there are companies like Nokia, which is extensively, working on this area. It's a parallel network, to be very honest. It's whatever current internet, it is exactly the replica, or maybe it is more sophisticated and try to become an organic systems. This is what the whole approach is. But first and very important thing is that we should be knowing where our cryptography for this particular transition that has to happen. And it is not a one time. Now we have to keep monitoring, because quantum computers and computing community is coming up with the hardware, software, and you are AI. We have to keep a watch on, on this development as well. And then also keep on developing our solutions, which can, always one step ahead of the attackers. For this, we have to keep our underneath infrastructure ready. And it is not a task of 1 or 2 years. It is going to take a lot of time for this whole transition. This is what the Deloitte has put up, and this is my proprietary, which we have given to Department of Telecommunication, which got published last year, that how the transition should happen, right? First and very important thing is that people should aware. I mean, I personally feel that research and the faculty community, academic community has to have this understanding, because the source of the skill professionals that we require, this is not for anybody's job, right? It's we need a skilled professionals, and for that we have to have this awareness even in the academic institutes. Research already is going on, and the industry. So awareness session is the first thing. Then there are certain steps those are involved into this, which is called as the cryptography bill of material, what I was trying to explain previously. Know your cryptography, where it is, what it is, which data it is, which application it is, which systems it is. Then do risk assessment. Then design a roadmap, how we wanted to do in transition. See, because, it's all about money. And trust me, now I've seen industry closely. Cyber security get very less budget. You have to manage until there is an attack and data is getting completely swapped off. There is a ransomware attack. People will say, okay, you please take care, manage your stuff, right? We have to have the roadmap ready, how the implementation should happen, so that the majority of the highly restricted data and the equipments will get safeguarded. We also need to train the employees and the academic institute on this. So we should have a training map ready, because it's an evolution. It's not a one time. Like we should be adding what are the new technologies that are coming, how we can be doing transition, what are the developers thinking, what are the libraries those are available, a lot of things. Once this whole chunk is ready, which is around 70%, then we can start the migration plan. That is the actual implementation. As it is a crypto, as it is at the niche, as is it as very, bottom, continuous monitoring is very important, whether it survives, fails. We cannot directly push the applications into the production. It should be into the sandbox. And then once it is stable, it can go into the production or actually live, right? Whole process is not a technical journey. There are a complex structure when you will see the organizations that many business units are working together, although there are different units, right? Different unit heads. So it's a strategically we have to tackle this problem, not only the technical. So everybody in the organization has to know that this transition is going to happen. So it's a whole process. The way we are going from classical or digital world to a transformational journey into the quantum. Similarly, we have to do this strategical or journey, not the technical journey. There are certain regulations, policies that had come across the world, and this is first thing that they have already given by NIST that you have to start this transition by 2022, and we are in 2025. People have already started across the world, and we are also trying to match the pace. India certainly has given out the deadline in advisory in July 2025 that you should be at least ready with CBOM so that we should be able to uh, design the migrations, right? And then maybe we can start the implementation. Of course, Europe, US, Canada, Switzerland, they are also given a lot of recommendation guidelines, and now they are putting up the regulations and the policies and laws. They are coming into the picture. Very first example, I would like to say the financial industries are going into rapid transitions, right? So because they will be get hit by adversaries faster after the defense. So this is one, but slowly people started realizing that it will be attacked on all these other sectors as well. So it's a rapid movement that is picking up from the quantum safe perspective. And there are certain community which is in the quantum computing area, which is trying to help so that we can build a robust, resilient, the quantum cyber network so that we can take care of our data, our lives. That's what I always feel, that it's not only the data, because our data is connected to the our lives now, right? So yeah, there's a lot to discuss. I'm so sorry, but yeah, I would like to stop here and I would like to take your questions if you have any. Thank you so much.
Yes, participants, if you have any questions, then please.
I mean, it's a wonderful presentation, very swift and very depth.
Thank you so much, sir.
You mentioned that there are a lot of associations which can help in the PQC, post-quantum. I understand the preparation for the post-quantum migration is very important. Can you also share those associations where we can be part of the learning exercise?
Yeah. So first and very important thing is that PQC migrations, standards has been developed by NIST. They have their own group. Entire community across the world is participating. They have their NCOE. And then, actually they are floating a lot of projects where they are funding also. In India, of course, National Quantum Mission, they are also funding on these PQC efforts. Because algorithm, although they are developed by NIST, to be very honest, there are a lot of research has been done and people, they don't trust NIST because of the backdoors. NSA has a complete control, right? So China has their own development center on, they have announced they are developing their own algorithm. Nobody trusts China. European industry also started developing their own algorithms, and also India is trying to put their efforts, right? So Singapore and other industries. But right now our standards are ready. We can at least use along with classical. There are n number of use cases where you can actually, make this as a product and take to the industry, because industry is looking forward for this kind of products. Now, WhatsApp is one of the examples. So India wanted to have their own WhatsApp, messaging app, and it's a huge effort. I know that. But yes, there are a lot of places. I think you can contact NQM where you can actually get some of the fundings. But abroad, every time you will find out, you will just hit it, and people are actually asking for proposals.
Great. Thank you. Great hearing you. Would you mind sharing your details if
Sure,
somebody
sure,
wants
sir.
to get
Yes, of course, I'll share. Of course. I'm so sorry. I'll just put it into the chat. Will that work?
Sure.
Oh, this is my organization address.
We couldn't see it.
I'm just typing it.
Okay.
Oh, there is a mistake. Oh, okay. So yeah, you can contact anytime.
Yes, okay. Thank you.
Any other questions I would like to take?
You mentioned one Mr. Mehta, if you don't mind. You said he's contributing to this in a large manner. Which Mehta you were saying? At the beginning, you said.
Mehta. No, I couldn't catch you. Like.
At the very beginning, you mentioned is your mentor or you got impressed?
Oh, my professor. Oh, it's a Professor Sure.
Sure. Okay.
So, yeah, but he's a crypt analyst. He's not. He's the offensive side. So he breaks sides. Yeah. Yes. So we developed algorithm which is actually safeguarding the current cryptography, but those are the two patents we have developed. We're working on, but I'm actively working with them actually. I love cryptanalysis. This is the field this is my extreme passion. So I stayed in this field.
That is very much visible in the way you deliver.
Oh, thank you, sir. Thank you so much. Any other questions?
Yes, anyone wants to ask any question? Okay, if no question is there, then we can conclude with the session. Thank you, Dr. Shravani. Your session was really very informative and knowledgeable session. Your vast work area and your vast experience in quantum computing really gives us idea that what real challenges are there in quantum computing as well as what is the importance of cryptography in computing. During your lecture, you highlighted on cryptography in quantum computing. Then, what are the causes, risk, and impact factors of cryptography failure? You also mentioned what are the recent challenges in quantum computing. It was really a fruitful session for a day today. Now, on behalf of management of Vidyavadini College of Engineering, entire organizing team of this ATAL faculty development program, and on behalf of all participants, I would like to thank you. Once again, we would like to have one more session from you, ma'am. And I wish you, yes, definitely, ma'am.
I think I lost.
And I wish you. Thank you, Shravani, madam. I think some technical problem is there with the Sandhya miss. Thanks a lot, madam. So it
Thank you
was
so
really
much. Thank
great
you so
session.
much.
Thank you.
so
Thank you,
much.
madam.
Thank you for inviting me. I hope audience liked the session, and I didn't bore them.
And definitely, we would like to connect with you again. Thanks a lot.
Thank you. Thank you so much. Thank you so much, ma'am. Thank you so much. Take care. Bye.
Hello, Kulkarni sir.
Yes, am I audible, ma'am?
Yes, sir. Sir, I am Dr. Amruta Ruperi, coordinator of this FDP. I welcome
Okay.
you, sir, and thank you for accepting our request and ready to deliver the session. Thanks a
Yeah.
lot, sir. Now I invite Sandhya madam. She will take over the session, start with your introduction, and then you can start the session, sir. So,
Yeah.
Sandhya madam, over to you.
Yes, ma'am. Yes. Thank you, ma'am. I welcome you, Anand sir, in this last session of this today's FDP. Welcome back all the participants. And before Anand sir starts, I would like to give the brief introduction about this Dr. Anand Kulkarni sir. Dr. Anand Kulkarni, he is an accomplished academician and researcher currently serving as an assistant professor in the Department of Electronics and Communication Engineering at the Institute of
Ma'am, you are not audible. You are not audible.
Am I audible, ma'am?
Now you are audible. Yeah.
Okay.
Ma'am, turn on your video feed so that we can hear you properly. I think there is some bandwidth issue you are facing from your side.
It's on, sir.
Now, Sandhya
Turn
madam,
off your
start.
video feed and continue with the introduction.
Okay. Okay, so let's continue. So Dr. Ananta Kulkarni, currently he is working as an assistant professor at Institute of Technology at Nirma Institute in Ahmedabad. With a rich academic journey spanning over 2 decades, he has significantly contributed to a teaching, research, and institutional development in engineering institutions. Dr. Kulkarni on his PhD from IIT Roorkee in 2020, specializing in spin torque based quantum computing architectures. Dr. Kulkarni holds 2 master's degrees, MTech in Microelectronics and VLSI Design, and MTech in Electrical Engineering, reflecting a strong multidisciplinary foundation across electronics, VLSI, and power systems. His research interests include quantum computing, spintronics, quantum gate design, neuromorphic computing, and circuit optimization. Dr. Kulkarni has published extensively in leading international journals such as IEEE Transactions on Magnetics, IEEE Access, and IEEE Transactions on VLSI Systems, with some of his work featured on journal covers for its impact and novelty. He is also a co-author of a Springer book on next generation spin torque memories and has presented at prestigious international conferences, including SPI Optics plus Photonics in the USA. In addition to his research contribution, he is an active speaker delivering expert sessions for organizations such as Citibank and numerous academic institutions. His previous academic roles at FCRIT Navi Mumbai and College of Engineering Ambezogai included student mentorship, research guidance, and leadership in several institutional committees. I welcome you, Dr. Anand Kulkarni, sir, and I request you to start with the session. Sir, over to you.
Thank you, ma'am. Am I audible?
Yes, sir. Yes, sir.
Okay, thank you, ma'am. I'm very much thankful to Sandhya ma'am and the entire team of Vidyavardhini College for giving me an opportunity to deliver a talk on quantum computing, that is a spintronics based rather. Before I start with my talk, before I start with my presentation, as this is the last session of the FDP, am I right, ma'am?
Yes,
Sandhya
sir.
ma'am,
Yes, sir.
this is the last
Yes,
session
sir.
of the
Yes, sir.
entire FDP, na?
Yes, sir.
So before I before I start delivering my talk, I would like any one of the participants to just summarize what they had covered in the entire FDP before my presentation. Any participant can turn on the camera and just summarize it, what they have earned. Anyone turn on the camera and please, you have 2 to 3 minutes to start speaking.
Yes, participant.
Just summarize in 5 to 7 minutes, not more than that.
So we have been introduced with the quantum computing.
Just turn on your camera. Just turn on your camera.
Comparison between the quantum computing and the classical computing. Then
Yeah.
quantum teleportation. Then how quantum is different machines are there. Then India may where places, which places are working on quantum computing. And some lattice algorithms, some mathematical concepts. But since we are very new to it, we are not yet confident. What we have heard is we forget easily. Like, so you, I request you that you don't consider that we are master in it. It's not like we are hearing
No. Just I wanted to know what you have earned through the 4 or 5 days. Just I wanted to know. I'm not saying that you are master. Even I am not also not master of the subject. I was curious enough to know what you have earned throughout these 4 or 5 days.
Basics of quantum computing, sir.
Okay.
And
have you gone through any
applications where it
implementation
is
of
used,
quantum
sir.
computing?
Yes, sir. We were being introduced with tools like Q in Universe and Q-tip and Qiskit also. One madam has explained one program also. She has explained statistical data. And altogether, starting from qubit, what was a qubit, and then the mechanics of dynamics, she has explained us all these teachers who have been coming over to us, and then the teleportation and
Algorithms
entanglement
were simulated on tools.
Okay, just
and
turn on your
quantum
camera and speak.
entanglement.
I'm not able to know who is
Basic
speaking.
gates.
Yeah.
Quantum gates.
Okay, that thing is also
Quantum
covered.
gates. Yes,
Okay.
quantum gates and Grover's algorithm also have been explained to us.
Okay.
And then this some statistical data algorithm program she has executed to us and shown, and how to register into Q universe and how to execute, that also have been explained. And variational quantum classifiers that also have been explained. Parameterized quantum circuits also today morning session have been explained.
Okay.
And then also the difference between classical cryptography and quantum cryptography, and how to prepare a shared data, shared keys, prepare a shared keys by, and how to have a correction of all the keys, and how to prepare a key also have been shown to us, sir. Like
Right.
zero means this direction.
So you are
Basis.
you were towards the quantum communication, teleportation, and cryptography. Mine will be
Yes, sir.
very different from these things. I will be targeting on the implementation of the quantum computing on one of the platforms, that is Spintronics. So the approach will be same, but in a different direction. Let me share my presentation and let us start. Is my screen visible?
Yes, sir.
Visible, na?
Yes, the screen is visible.
Yes, sir.
You can full screen the presentation.
Just a minute. Yeah. Is this visible?
Yes, sir. It's visible.
Yeah. Thank you. Thanks a lot. So I'm very fortunate I have got an opportunity to speak before you people. I mean, my talk will be on spin torque based quantum computing. I'm an assistant professor at Nirma University. What happened? My presentation outline, I will be beginning with the introduction. That introduction will cover history of computing, and a need for quantum computing. Then I will talk about quantum computing in brief, as you all people have gone through the different basics through the entire FDP. Then I will not cover applications, that time is very much limited. I will directly go to the implementation of quantum computing. That I said in the beginning. The approach will be same, but in the different direction, that toward the implementation of the quantum computing. In that we will see Divinzo's criteria and how it is applicable to the spintronics also for the physical implementation. Then I will share what research I had carried out when I was at IIT Roorkee, and after that also after 2020, what I have done in this particular area. So I will be discussing with you the transmission coefficient, matrix modeling, then elementary quantum gates reduction, then Boolean logic quantum circuits, reversible D-latch, quantum Fourier transform, Toffoli gate based full adders, that is reversible computing, then quantum multiplexer, control V and V plus gate. There are some kind of a gates. Probably you would have seen in the basics of the quantum computing. Then we'll be talking about future of quantum computing, followed by the conclusion. Before we nowadays we are much talking about VLSI and India's growth in VLSI, chip design, chip making, AI and chip, so many things. But before we move on with the quantum computing, we need to understand why quantum computing is required. What is the necessity of quantum computing? For that purpose, we need to move from the scratch towards the quantum computing. So we need to understand first generation of the computers. It was started in 1951 and ended in 1959. Then it was started, there were no diodes and transistors and all those things. There will be universal AC machines. Can you imagine, it was a kind of a room wherein a vacuum tubes in 5,600 numbers, crystal diodes of 18,000, relays 300, and the rate was 2.25 megahertz, and storage is of 1,000 words only. In a word file, you can write the 1,000 words in a half an hour, or what we can say an hour almost. But in those days, to write the 1,000 words capacity, you need to have the 5,600 vacuum tubes, 18,000 crystal diodes, 300 relays, bit rate of 2.25, and that was only possible to store 1,000 words. The heating issue is again a separate kind of a thing. Then the generation is moved from the first generation to the second generation computers, that is from 1959 to 64. It was a paradigmic change or paradigmic shift in the entire VLSI domain. Why? Because transistors were invented at the Bell Laboratory. Now you may ask a question, what is the difference between a vacuum tube and a transistor? The basic difference is that they are reliable. Increase the computational speed, volume and cost reduction, and less power consumption in comparison to the vacuum tubes. Then we moved from the second generation to the third generation, that is 1964 to 71. It was an era of integrated circuits. Nowadays we call it as ICs. They are more reliable, very cheap. For example, microprocessors are there, microcomputers are there, and mini computers are there. Now you may ask a question, when the transistors were invented, why to have the ICs? If some of you are electronics engineers, you must be knowing the breadboards. On breadboards, you can have the discrete components. But for making a complex circuit, you need to have a integrated circuit. So the third generation of computers was from 64 to 71. More reliable, very cheap, microprocessors, microcomputers, and mini computers. Then the fourth generation, which was from 1971 to till today, that is single silicon chip, which has VLSI, circuits packaging, memory chips development. You all are aware of nowadays, it's buzz. Everywhere go, you will only talk about the VLSI and boom of VLSI. Why? Because of this fourth generation. Now the question comes, why there is a need of quantum computing? The need of quantum computing is that integration density limitation in classical computing architectures. Probably you would have heard of Moore's law. The Moore's law says that every 18 months, the number of transistors on the chip gets doubled. Now, if I'm doubling the chip is the same, I'm doubling the transistors. The transistor size is also decreasing, but at the same time, interconnect size is increasing. So again, it's very difficult to increase. So we talk about the beyond Moore and all those things. And one more important thing is that power dissipation, irreversible Boolean logic based circuits is a big issue. I will come to that. And This is kind of from the fabrication, from the physical kind of a thing. But when we talk about the problem solving, classical computing could not solve complex problems efficiently. For example, number factoring or number searching, those kind of a problems are very complex when we try to solve it classically. So the one way out is the quantum computing, which has the ability to solve the complex problems efficiently. Now, what the quantum computing is all about? We had heard about the classical mechanics, and we are nowadays we are discussing about the quantum computing. We need to compare the principles of classical mechanics with the principles of quantum mechanics, that through the postulates. Now, what these postulates in the quantum computing? Any physical system is described with the state space of the system. By now, you would have heard this word, state space, while studying the basics of the quantum computing. The most important thing is the Schrodinger equation, Schrodinger cat. What it shows? The time dynamics with the Hamiltonian. Then one of the important aspects is the measurement in quantum computing. If you take a simple circuit and you want to measure the voltage, you can put a probe of multimeter anywhere and you can measure the voltage. No harm in that. You are able to easily measure the voltage. Why? Because the circuit is big, discrete. When we talk about the quantum circuits, when you talk about the quantum measurement, they are at the atomic level. And when you try to measure, try to trace, the entire system gets collapsed. So measurement is a big issue in case of quantum computing. And this, as I said that in the first postulate, state space. Now let me tell you what the state space is. State space is a combined physical system, or is a tensor product. It's not the simple product, it's a tensor product of the space of individual constants of physical system. There are two different physical systems are there. When they're combined, they are in the form of state space represented by the matrices. Now the qubit, as I said, you all have gone through this, just I'm repeating this thing and I'm quickly coming to the important or the focus of this talk. It is a fundamental unit of quantum computing and quantum information. For example, what these qubits representations are: photon polarization state, two energy levels of electron around the atom, and electron spin. It's a vector quantity. It's a Bloch sphere, state space of qubits. The exterior of the sphere represents the pure state, and interstate represent the mixed states. They're represented in the columns and vectors. 1 0 0 state, 1 0 0 1 state, 1. So qubits exist in the superposition of a linear combination of states. And most important thing is a quantum collapse. As I said, that quantum computing has the ability to process the information, large amount of information parallelly. But when you try to trace the quantum information, try to measure the output, the information will be converted from the quantum to the classical. But at the same time, the disadvantage that there is a quantum collapse, there is a loss of information. That is a big concern. Now the one qubit gates and poly gates. Basically, you have gone through all these basics. Just I'm repeating all these things. Poly gates are nothing but rotation around the x-axis, rotation around the y-axis, and rotation around the z-axis of a state. Then identity gate. Identity gate means 1001. No effect on the, what we can say, that qubit state. Not gate, just state is inverted. Phase shift only phases, and Hadamard gate is very interesting. This gate is very interesting. Why? Because this gate has the ability to transfer the information from the classical to the quantum and from quantum to the classical. If you find any Boolean circuit, reversible circuit, you will find Hadamard gate at the beginning and Hadamard gate at the end. The reason is that these two Hadamard gates are the interfaces of the classical to quantum and quantum to the classical. So these are some of the one qubit gates. Then two qubit gates are there. The first two qubit gate is control not gate. If you look, you have gone through this probably during the last 4 or 5 days. What this control not gate says, now there are two qubits, A qubit and B qubit. And at the output side also A, and but at the second is A tensor B. What does it mean? If A is in state 1, then B is inverted. Simple as that. If A is in qubit state 0, B will remain as it is. And control unitary gate means what? If A is 1, some kind of a unitary operation which is specified in that block will be acted on the qubit B, and that is UB. Now next is the Toffoli gate. Toffoli gate is also called as control not gate. What this Toffoli gate is all about? Just look at, there are 3 qubits, A1, A2 and B. If A1 and A2 both are 1, remember this very carefully. When A1 and A2 both are 1, then only B is inverted. Otherwise not. The basic difference between Toffoli gate and CNOT gate is, in case of CNOT gate, there is only one control. In case of Toffoli gate, there are 2 controls, right? The reversible computations are performed by universal Toffoli gates. And the most important thing is that when we talk about the physical implementation or the decomposition of any quantum circuit, from the CNOT gate to the Toffoli gate to the Fredkin gate and all those gates, you need to decompose it based on which technology you are going to physically realize it. That is a very, very important aspect. Now, let me come to the reversibility and irreversibility. Before I move further, I would like to ask a very simple question to you all. Which, now all of us are aware of the classical computing or classical gates. Which gate is reversible? Anybody please answer. Which gate is reversible? Participants. Hello? Am I audible?
NOT gate, sir.
Yes. Why? Your answer is right, but why?
It changes, yeah, sir, because it changes the values.
No, answer
Inverted
is not right.
values.
Your
sir.
justification is not right. Why not gate is, there are several gates. AND gate is there, OR gate is here, NOR gate is there, NAND gate is there, XOR gate is there. But why NOT gate is reversible? What must be the reason? Your answer is right, but justification is not right.
For decision making kinds of
Okay.
things, sir.
What?
Decision making, whenever we have to
No,
make
not
some
it is not
decisions.
a thing of decision making. It is something related to the information loss. Just try to do any other participant.
Sir, applying the same thing will get the original value.
Applying
Applying not again for the value will get the original one. That's why we can say it as a.
again, answer is right, but justification is not right. Any other participant? Let us try it more. Let us try it more. Shall I answer? Okay, I will answer. If you look at the NOT gate, if I apply 0 at the input, I get the 1 at the output. If I apply 1 at the output, I get 0 at the output. What does it mean? If I just look, if I look at the output, if it's 1, I'm certain that input was 0. If it is 0, I'm certain that input was 1. Just by looking at the output, I'm 100% sure that what was my input. But the same is not applicable to all remaining other gates. Take you example of AND gate, OR gate, NAND gate, NOR gate. Just by looking at the input, you are not sure. You are only, you can predict, but most of the time predictions are wrong. So that is called loss of information. You are not able to predict what were my inputs so that I have got this output. So this kind of a problem is there. That is called loss of information. And 1 bit loss of information results in heat dissipation of KTLN2. That is given by the Landauer's principle. What it is? KTLN2. K is Boltzmann's constant. That is 1.38 into 10 to the power of minus 23. T is the temperature, a natural log of 2. Right? So if we see at it in a larger perspective, high information loss in complex irreversible circuits. So many transistors are there which are required to design the OR gate, NAND gate. I mean, when we talk about arithmetic logic in it, memories and whatever it may be, high information loss in complex irreversible circuits that results in heat dissipation. Someone is saying anything? Speaking something? And therefore, Boolean gates are all Boolean gates are irreversible except NOT gate. So quantum gates measurement process operation is irreversible. Why? Because the moment you try to trace the information, the entire quantum information is lost. That's why quantum measurement is irreversible. Operations are not irreversible. For if you want to go into the deep, you can refer the Landauer's paper, Irreversibility in Heat Generation in the Computing Process by the IBM. Now let us talk about quantum circuits and algorithms. They are very much similar. A quantum circuit is a structure of unitary operations and measurements on a n-qubit state. And they are actually sequence of operations, sometimes information in parallel, sometimes operations in parallel. A quantum algorithm is stage by stage process where each of the stage can be executed throughout a circuit. As I said in the beginning, quantum computing has the ability to solve the complex problems in comparison to the classical problems. Two such problems I would like to present here. Shor's algorithm, it is dedicated for the number factoring, and Grovel's algorithm, searching formless database or an unordered list. You can refer the P.W. Shore's paper, Polynomial Time Algorithms for Prime Factorization and Discrete Logarithms on a Quantum Computer. And one more paper by the Grover for the Framework for Fast Quantum Mechanical Algorithm. These two papers are very interesting to go into the depth for the Shore's algorithm, that is for the number factoring and searching formless database or an unordered list. Now the question comes, now just we have gone through the, in brief, not in detail, small basic gates and reversibility, irreversibility. The question comes, how to implement the quantum computing? With the help of the classical hardware, conventionally, like the system on chip and all those things, or quantum hardware, and why? That question comes here. The reason is that when we talk about the implementation of the quantum computing, we need to talk about the physical implementation of the quantum computing. Divinzo has given one criteria. If any technology, any quantum computing realization technology is able to realize, able to obey these criteria, then only the implementation of the quantum computing with that physical system is possible. Otherwise, not. It's crystal clear. Which those criteria? The first one is storage of quantum information. The information is encoded in classical system till the computation is performed. If it is there, then only physical implementation is possible. Initial state preparation, just like collecting the things to prepare the tea. Initial state preparation. The state of all qubits should be set to 0 before computation begins. Next, isolation. Isolation means I'm sitting in an AC room and I'm completely isolated from the outside. I'm very much secure. The isolation of the system from external environment needed to reduce the decoherence effects. Probably would have, one of the speakers would have spoken about the decoherence effects. Now it is defined as the loss of information from a quantum system into the environment, just kind of a decaying process. Quantum gate implementation. What it is? For the realization of the quantum gates or the logic, I could say, the individual qubit state isolation, manipulation, and interactions are required. Controlled interaction, not uncontrolled. Moreover, the gate operation time should be less than the decoherence time. If this is possible, then only quantum gate implementation or quantum algorithm or entire system is able to be implemented. Last but not the least, the most important thing is the readout or quantum measurement. Now, the scalable physical system or the technology should have measured the final state of qubits at the end of the computation to obtain the output. If you want to go into the depth for this particular Divinzo criteria, there is one paper by the DP Divinzo, the physical implementation of quantum computing, which was published in 2000. Probably you may go through it. Now, what the physical implementation? I said that information encoding, state initialization, isolation, implementation, measurement. Now, I need to clear one thing very clearly here. When we talk about the classical computing and implementation of the classical computing, only we talk about the transistors, only we talk about the semiconductor, that is silicon, germanium, 350, and all those things. But when we talk about the quantum computing, there are several different modes of physical realization. For example, dipole trap is there, stationary and flying qubits are there, optical fiber coupled cavities are there, superconducting qubit. This superconducting qubit is the basic unit of the IBM base realization. It is a superconductor based. Then cavity based quantum network is there, quantum dots is also there. These are some of the different kinds of the technologies which are through with the help of which we are able to realize the quantum computing. The question comes, which one is better? Everyone has a pros and cons. So when I was doing my PhD, I switched to the spintronics. Now, why spintronics? Spintronics, before moving to the realization, we need to understand about the spintronics. It's a quantum mechanical spin of an electron. The spin creating a magnetic moment which is called pseudo vector. If you look at it very carefully, in any material, the spinning electron is rotating around the nucleus. There are two rotations. One rotation is electron is spinning about around itself, and electron is also spinning about the nucleus. So that electron has its own spin magnetic moment and one more orbital magnetic moment. The entire thing is based on the interaction between orbital magnetic moment and spin magnetic moment. The behavior of an electron spin and charge, spin magnetic moment, solid state devices are studied under the spintronics umbrella. For example, non-volatile data store, you would have heard of the MRAMs, magnetic random access memories, high integration density, information processing at high speed, and low power consumption. If you want to go into the depth, you can go through the two papers. One is by D.D. Tang and Wiley, Magnetic Memory Fundamentals and Technology, by the Cambridge University Press in 2010, and L.I. Ing, Dissertation on Mechanics, Mechanism and Assessment of Spin Transfer Torque Based Memory. It was published by the Massachusetts Institute of Technology in 2009. These are some of the fundamentals. You can go through these papers. Now the question comes, how to do the physical implementation with the help of the spin torque based quantum computing architecture. There is a one group at Purdue University that groups actually started working in this area, that is spin torque based quantum computing architecture. They just proposed a structure of 4 qubits, and basically these 4 qubits are reconfigurable. Reconfigurable by means on both sides of any qubit barriers are there. So that structure has the ability to isolate the qubit, the structure has the ability to manipulate the qubit, the structure has the ability to interact between 2 qubits or any 2 qubits, no issue. So if you look at this particular structure very carefully, there are low barriers and high barriers. Spin coherent semiconductor channels are there. So 4 qubits, S3, S2, S1, S2 embedded in a spin coherent semiconductor channel. The static qubits could be 29 silicon nuclear spin, 31 phosphor donor level, electronic donor spin or nanoscale magnet embedded in the semiconductor, right? So the spin potential generated by magnetic contacts, giant spin Hall effect. I will come or spin pumping at low and room temperature. Now, how this happens, just look at the structure very carefully. There are two reservoirs. One is upspin reservoir and the other is a downspin reservoir. So they are pumped into the towards, not into the channel, towards the qubit. Barriers are lower, so these electrons are interacted, spin polarized electrons, I could say, interact with the qubit and they change the state of the qubit. If you look at it very carefully, there is one D0 distance. The D0 distance is measured from the barrier G1 to the center of the qubit. So I'm not going into the mathematics of this as time is not permitting. Just only I could talk about this tan alpha. This alpha is the interaction coefficient, the ability of the spin polarized electrons to interact with the qubit. It depends on the distance between center of the qubit and the barrier. Then exchange interaction, that is G, and several things are there. K is the kind of factor which is responsible for this interaction. So just look at it. Just I had implemented this. This is the existing work. This is not my work. How to initialize the qubit from the 0 to 1. That is qubit initialization, qubit rotation. So these two equations are there, Sz of n and St of n. One for the initialization, second for the rotation. Now just look at it. Exist 2 qubit entanglement, S0, S3, T1, T2, R1 is equal to T1 minus IB and I8. This is mathematics. If somebody is interested in carrying out this work, they could contact me. Now, this is entanglement. But what is this entanglement? Basically, there are two operations. First qubit rotation, one qubit rotation, and two qubit entanglement. In two qubit entanglement, the electrons are injected in such a way that both qubits reach a same state, which is called the entangled state, two qubit entanglement. Now let me share my work with you, transmission coefficient matrix modeling of the spin torque based n qubit architecture. So why we found from this Purdue University group research group, investigation of effects such as ratio of reflection barrier height to exchange interaction on quantum operations was not considered. A fully specified or general matrix-based general methodology utilized for the spin torque based n-qubit reconfigured architecture. Moreover, for the fault-tolerant quantum computing, an optimized quantum library is essential for every physical machine description. As I said in the beginning, there are different technologies, different technology. So the entire mechanism is different for different, same mechanism is not applicable to each, and no optimized quantum gate library is introduced for the same spin torque based QC. So this work includes modeling of modified matrix based single qubit rotation, two qubit entanglement for n qubit architecture. This is our architecture, this is our design. We introduce the two transistors T1 and T2 for the Hall effect so that we can inject tunnel barrier. This is high barrier, low barrier, and spin qubit. And the semiconductor channel is there. So there's a single qubit architecture wherein two switches are provided, switch 1 and switch 2. These two switches are the role of the switch 1 is to inject the electrons and to magnetize through the spin Hall effect, and then role of the second switch is to inject these spin polarized electrons into the channel to reach the qubit so that qubit state can be changed. But there are two kinds of times, time 1 and time 2. One is called relaxation time 1, second one is called coherence time 2. What these two, if you look at this blast sphere carefully, one is a vertical time, another one is a horizontal time. What is the vertical time? The time required to reach from state 0 to state 1. But at the same time, we need to talk about the coherence time also. That is called dephasing time. In the XY plane, the variation angle phi and theta and phi depends on T1 and T2 respectively. In silicon, T2 is comparatively shorter than T1 for donor electrons. I'm not going into the details, just I'm telling you the major source of decoherence in architectures is when electrons moving in semiconductor channel that again depend on the material of which semiconductor channel is made up of and temperature. Isotopically enriched 28 silicon doped with phosphorus is more significant than other forms of silicon due to its long enough coherence time. Now, we had modified the transmission coefficient matrix from the Purdue University group to by us. We added few effects in that. So this is our design. TS singlet and triplet basically, where X is the reflection barrier height divided by exchange interaction. So this is our design, that is singlet and triplet transmission coefficients. This we had designed. Now, as I had shown, this is a single qubit rotation and we had obtained how the effect of reflection coefficient to exchange interaction on the rotation. And we had obtained 12 different, obtained from the 12 different values from 0 to 12 along the x-axis, along the z-axis. What we observed, if you go on increasing the exchange interaction, this ratio, barrier to the exchange interaction from 0 to 12, the number of electrons required are reducing. If you look at it very carefully, you are reaching the zero value very quickly as we go on increasing the number of electrons. That is by common sense. I mean, if I need more rotation, I need to introduce more electrons. This is a exchange factor alpha. As I said that if I go on increasing this ratio from 0.01 to 1, this interaction goes on increasing. But if you observe it carefully, it is saturated at 0.8. It is not further increasing if you go on increasing beyond 1 also. So the maximum value is this one. N alpha variation, if I go on increasing the angle of rotation from pi by 2 to pi, and on the y-axis it is log to the base 10 n alpha by pi, what I have observed, this interaction is increasing. That is n alpha variation is increasing. Now this is the 2-qubit architecture. 2-qubit architecture is for the 2-qubit entanglement. If you look at it very carefully, only switching mechanism is provided at the bottom of one of the qubits, not both qubits, right? So this is switch 1, this is switch 2. So electrons are injected from the switch 1, from the qubit 1. They interact with the qubit 2, they are interacted with the qubit 2, they travel it further, and they interact with the qubit 1, again come back, again qubit interact with the qubit 2, and they are in this interaction happens till they both reach in the same state. The entire thing depends on the distance between these two qubits, that is D12, which is in between them. The barrier 1 is there, this barrier 1 has to be lowered, right? So this is a 2-qubit entanglement. As I had showed in the beginning also, we have reduced the number, or we have model it in such a way that the number of electrons required to get the entanglement is reduced. If you look at it very carefully, it is from 0.1 towards the as exactly half between 0 to 0.5. So, and it again depends on what is your interaction value. Now, this is a error probability. What we observed, the other side of the coin is that if though we are increasing the interaction with our model, but what we observed that error is increasing. If you look at it very carefully, this blue is represented by the previous model, and all other things are added by us. Remaining colors are added by us for different values of barrier to the exchange interaction ratio. Now, let us try to understand the problem elementary quantum gates reduction for the spin torque based n-qubit architecture. Now the question comes, convention reduced decomposition quantum circuit utilized to evaluate the performance of the quantum gates in terms of how the performance is decided, the number of elementary gates. It's a simple thing. I always, as I said in the beginning also, coherence time is there. So always try to achieve a quantum system operation with the minimum number of elementary gates. So my target always should be I need to have a design in such a way that I will have minimum number of elementary gates so that I could quickly carry out that operation within minimum time. Gate fidelity. What this gate fidelity means, I know what my input, I was knowing that what is my expected output. Now when I get the actual output, how much close it is to the original output, desired output. That is called the gate fidelity. Sometimes you get 95%, sometimes you get 99%, but never you get 100%. Several reasons are there. And execution time, number of interacted electrons, and the fidelity. There are several formulas for obtain the fidelity. Rho-d means desired fidelity, rho means actual fidelity. So this F stands for the fidelity. Now let us talk about realization of reversible quantum gates with the help of our own what we can say that spin torque based qubit architecture. This is a single qubit operation. Simple circuit is there. Hadamard gate is, as I said in the beginning, in reversible computing, Hadamard gate is always present at the beginning and Hadamard gate is always present at the end. So this Hadamard gate, there are several ways to realize this Hadamard gate. The conventional way which was provided by the Purdue University group is XZX. What does it mean? Rx pi by 2, Rz pi by 2, and Rx pi by 2. 3 rotations in sequence. So what happens if you look at it very carefully? Just look at the graph. First, we have rotated around the x-axis by pi by 2. Then we have rotated around the z-axis by pi by 2. Then we have rotated around the x-axis by pi by 2. So it has reached from -1 to 0. Then it is along the 0. Second one is 0 to again 0. Third one is 0 to -1. So this way you achieve the Hadamard gate. So basic role of the Hadamard gate in the entire quantum computing or even quantum communication, wherever you apply the Hadamard gate, the role of the Hadamard gate is to transfer the classical information into quantum information and quantum information into the classical information, right? Now the 2-qubit operations. This kind of a structure was given by Purdue University. This is basically decomposition. As I said crystal clearly in the beginning, every realizing technology has its sequence of operations. If I'm doing it by the spin torque, it will have a different set. If I'm doing by the quantum dots, it will have a different set. If I'm doing by IBM's, what we can say that superconducting, it will have a different kind of a set of operations. So nothing is unique. That is for clear. So as far as this particular technology is concerned, the initial framework had suggested 11 operations. So RX, RZ, RX, RX, RZ, RX. And in between that, two under root swap operations, one Z operation, one S plus operation, and one S operation. Probably by now you are aware of all these operations. If you look at this very carefully, now I have applied this green color. The green color is the control qubit, and red color is the controlling qubit. Sorry, red color is the controlling qubit, and green color is control qubit. If you look at it, green is moving from -1 to +1 only when green is, sorry, red is moving from -1 to +1 only when green is -1, otherwise not. If you look at it very carefully, these 11 operations are, with the help of these 11 operations, I'm able to realize this control not gate. What this control not gate says, if A is true, then act on B, otherwise not. Keep idle. Then 2-qubit operation control not get reduced. So what we have done, we have designed in such a way that we have reduced this 11 from 11 operations to the 7 operations, minus ry pi by 2 to ry pi by 2. We have replaced these 3 operations at the beginning by minus ry, at the end plus ry, right? So just look at it very carefully, number of electrons. So just compare these two. If you are able to see it, just compare these two. And thanks to this CC paper by the Princeton University, with the help of which we will be able to reduce these 11 operations into the 7 operations, that is optimized quantum gate library for various physical machine descriptions. Now the 2-qubit operations, this is a swap gate. Swap gate means what? A will become B and B will become A. For that purpose, we have used the swap gate in 3 sequences: first C0 gate, second C0, third C0 gate, with the help of which we will be able to swap the states. S2 becomes S3 and S3 becomes S2. Now this is a reduced swap gate. This is a conventional with the help of the Purdue University. This is our 2-qubit operation. We have made S2 equal to S3 and S3 equal to S2. This is Toffoli gate conventional. This is Toffoli gate reduced. If you try to compare these two, I will provide the chart at the end how the comparison is there. This is Fredkin gate. Fredkin gate is controlled swap gate. It has 3 qubits. 1, 2, 3. If 1 and 1 is 1, then 2 and 3 are swapped. This is a general way. This is our way, reduced. Now the performance evaluation and comparison. In conventional, the control not gate was realized by 11 operation. In our methodology, it was reduced to the 7. So the percentage reduction is 36.36. In swap gate, in conventional, 33 operations are then reduced, 21 operations are there. Again, the similar kind of reduction, 36.36. Toffoli, 79 operations, 51 operations, 35.44. Fredkin controlled swap. In convention, it requires 101 operations. It is drastically reduced to 65. The reduction is 35.64. The average reduction number of element operations is approximately 36%. So the average gate execution time is reduced by 10.58%, 13.77%, 14.30%, and 12.92% of control not, swap, Toffoli, and Fredkin gates respectively. This is called quantum cost basically. Whichever number we present for the realization of any gate, that is called quantum cost. That is called quantum cost. Now in terms of yes, anybody saying anything? Yes? I'm not able to hear you. Can you speak loudly? Ma'am, I'm not able to hear you. Please speak loudly. What you are saying? Can you repeat the question? Hello, madam. Can you repeat the question? Am I audible?
Yes, sir, you are audible.
Ask the question.
Sir, I think by mistake her mic was open.
Okay, okay. I was thinking that someone was asking the question. Okay, no issue. Right. Now the fidelity, if you compare it with the conventional reduced, for the C0 gate, fidelity is improved from 99 to 86 to the 99.94 to 99.92 in both cases. If I consider the ratio and if I don't consider the ratio, we have comparison both way. Swap, Toffoli, Fredkin. So we can say that fidelity variation is comparatively less in case of C0 and swap gates. C0 and swap gates have gate fidelity well above the fault tolerant fidelity. All of them are almost above the 99, except Toffoli and Fredkin, a little bit reduced. Gate fidelity of modified matrix Toffoli and Fredkin gates is below the fault tolerant fidelity. What is the trade-off? The trade-off between fidelity and reduction in number of electrons. Existing matrix reduced gates have higher average fidelity. Modified matrix-based reduced gates require a minimum number of electrons. Modified matrix-based reduced gates achieve both better fidelity with reduced number of electrons. And quantum gate library for the spin torque-based architecture is RYRZ under root swap. Right? Now, optimal Boolean logic quantum circuit decomposition. Next problem for spin torque-based n qubit architecture. As I said in the beginning, also, what are the different factors for this reversible Boolean computing? First one is high power dissipation, irreversible computing architectures due to information loss. Second one is it has the inability to handle large data due to sequential information processing. Heat dissipation can be reduced by utilizing the CMOS-based reversible computing architectures. Quantum computing can circumvent these problems due to fundamental ineffaceable characteristics of quantum mechanics-based reversible computing and parallelism. Spin torque-based physical realization is the most suitable platform for the QC-based reversible computing due to electron spin analogous to the qubit. Optimal quantum circuits are required to physically realize the complex Boolean logic due to spin qubit decoherence and reduce the number of transistor switching activities for the spin generation and injection required for the spin qubit rotation. Now let us talk about optimal decomposition of the spin torque base qubit architecture, sorry, reversible Boolean. We had developed one module which called 2 qubit module, which consists of 2 under root swap gates, one Z gate, one is S plus, one S, and RY pi by 2. Next one, and we have realized with this model, the XOR gate, reversible XOR gate. If you try to understand this reversible XOR gate, A is A, B is B, and third qubit is 0. What the XOR gate is? A and B will remain same, but only third gate will be your final output. The same is here. Next is AND gate, reversible AND gate. A will remain A, B will remain B, and third gate is 0, which is called ancilla gate. Extra gate is extra qubit is added, and you get the output at F. This is the entire decomposition, reversible decomposition of the AND gate, and you get the evolution like this. This is the OR gate. It consists of one Toffoli gate and two C0 gates, AB0, ABF, right? AB0. So with the help of this, we are able to get it. Then half adder, it consists of one Toffoli gate and one C0 gate, sum and carry, right? So this is the number of electrons in thousands. Then this is a full adder. It consists of two Toffoli gates and two C0 gates. So we get it this way. This is a Boolean logic, and this is kind of a parallel processing. We have prepared some modules and we use these modules here to realize the quantum computing. The performance evaluation of all this reversible Boolean computing. Yes, we have achieved the reduction in number of switching activities, and we have AND gate, OR gate, XOR gate, NAND gate, NOR gate, XNOR gate, half adder, and full adder, which consists of 37.97%, 41.58%, 45.45%, 37.97%, 41.58%, 45.45%, 40%, and 40.55% respectively. So by carrying out these experiments theoretically rather, what we envision a decrease in power dissipation due to reduction in number of switching activities. Now this is a pictorial representation of entire analysis from the AND gate to the full adder. First order conventional, it is from 5.59 to 5.92. First order reduced 5.56 to 5.88. First order optimal, right? 5.54 to 5. Optimal means wherever the common gates are there, we have either merged or removed. Second order convention 5.5 to 5.84, 5.5 to 5.86, 5.5 to 5.82. Reduction number of switching activity of transistor is 37.97, 41.45, 41.58, 45.45, 37.97, 41.58, 45.45, 40% and 40.55 respectively. We also envision a decrease in power dissipation due to reduction in number of switching activities. Fidelity comparison. For AND gate, the fidelity is improved from 99 to 95 to 99.04, 99.0 to 98.8. Why? Because we have added the effects. That's why fidelity is reduced. If we consider the ideal cases, the fidelity will remain as 99 onwards, above it. So, but if you look at the half adder and full adder, there is a concern. For the second order means when we added all effects, the fidelity is reduced to 98.79. So this is a big concern in this kind of a technology because number of elementary operations is increased. So there is an improvement in gate fidelity for optimal decomposition of computing blocks in comparison to the reduced decomposition. There is an improvement in the fidelity of the optimal decomposition in the comparison to the reduced decomposition. Now let us talk about implementation analysis of spin torque based reversible delatch. Now, as I said that I had used the word optimization in the previous slides. Now, let me tell you what the optimization means. Optimization means, let us suppose that two gates having same kind of rotation, but in the anti-clockwise direction with the same angle, both gates will be removed and no rotation will be there. This is the first technique. And these techniques are not constant. It depends on how your circuit are designed, how your circuits are decomposed. When the circuits are decomposed, these things will come up to know how they are decomposed. Minus RY and minus RY, same opposite direction, but in the same way. So pi by 2 and pi by 2 becomes pi. Now two different gates. One is a yes daga pi by 2 and my now by now you must be knowing what the daga is by the bracket notations and all those things. Minus S daga pi by 2 minus T pi by 4. So it becomes minus RZ 7 pi by 4. So addition of angle is there based on how things are there. These are the optimization techniques to reduce the number of actual elementary operations required so that we can reduce the number of switching activities. So this is the optimal decomposition of the reversible delatch. So this is the realization of the reversible delatch for different states. You can see it thoroughly. Enable is 0, previous state is 0, reset, set, and all these things. So fidelity comparison without output state reduction. We tried it for the 5 different cycles, cycle 1 to cycle 5. It is from 99.52 to 97.24. Till it from 98.3 to 98.15. What we observed, if you go on increasing the number of cycles, there is a reduction in the fidelity. I could not say slight reduction because we have only considered the 5 cycles, and D flip-flop is such that you can use it over the cycles. As number of cycles is increasing, which results in small but incremental error at the end of each clock cycle. So what we theoretically did, we had added one component in the feedback that is called error correction. And what we observed theoretically, if we add this error correction, we got an improvement in the fidelity, that is 99.09, 98.83. So we can say that the average fidelity of the deep latch considered for the implement analysis at the end of the clock cycle is well above 97%. The fidelity is further improved by approximating the present state output utilized for the next state input. So this was about the reversible Boolean computing. Now let us move from the reversible computing to a different kind of a domain, which is called spin torque based quantum Fourier transform. What is quantum Fourier transform? We can use the quantum Fourier transform in Shor algorithms also. What the Shor algorithm does, it performs the integer number factoring in polynomial time, and the integral component of I could say this quantum Fourier transform is present everywhere. The integral component of the source algorithm is in quantum Fourier transform. The quantum Fourier transform applications are phase estimation, discrete algorithms, quantum key distribution protocol, multi-party quantum telecommunication, quantum arithmetic. The physical realization of quantum Fourier is very important and needs to be addressed. What we have done in this work, we have modeled the physical realization of the quantum Fourier transform with the help of the optimized quantum circuit. As I said that optimization is not fixed. It depends on how you